If you like the space and learn about its curiosities, consider subscribing to the channel. We have 2 videos every week. Thank you for your attention and enjoy the video. The universe is vast, enigmatic, and in constant flux, revealing new mysteries with each discovery we make. One of the most fascinating recent developments in astronomy is the detection of a potential second Earth in our galaxy, known as K2-18b. This planet orbits a red dwarf star located about 124 light-years away in the constellation Leo. It's not a new discovery per se, as it was initially identified in 2015, but what has captivated scientists recently is the detection of potential biosignatures in its atmosphere, which could indicate that life, at least in its most primitive form, might exist or could have existed there. K2-18b is categorized as a super-Earth, a type of exoplanet that has a mass greater than Earth's, but significantly less than that of ice giants like Neptune and Uranus. It lies within the habitable zone of its parent star, the region where liquid water could theoretically exist on its surface. This factor alone makes it an intriguing candidate for further study in the search for life beyond Earth. However, the recent observations using the James Webb Space Telescope have added a new layer of intrigue. Astronomers found evidence of carbon-bearing molecules, including methane and carbon dioxide, in the planet's atmosphere. These compounds are crucial building blocks of life as we know it, and their presence raises the question of whether biological processes could be contributing to their formation. The potential for life on K2-18b isn't as straightforward as it may seem. Unlike Earth, K2-18b is enveloped in a thick hydrogen-rich atmosphere, making its surface environment very different from what we're used to. While the detection of these molecules is exciting, it's not definitive proof of life. There are several non-biological processes that could also explain the presence of these gases. For instance, chemical reactions between the planet's surface and its atmosphere might produce methane and carbon dioxide without the need for living organisms. Nevertheless, the fact that K2-18b lies within the habitable zone and shows evidence of complex chemistry makes it a prime candidate for future missions aimed at unraveling these mysteries. In addition to its atmospheric composition, the size of K2-18b adds another layer of complexity. At 8.6 times the mass of Earth, it has much stronger gravity, which would likely have a profound effect on its climate, atmospheric circulation, and any potential ecosystems. This leads scientists to speculate whether the planet has an ocean beneath its thick atmosphere, similar to the subsurface oceans thought to exist on moons like Europa or Enceladus in our solar system. If such an ocean exists, it could provide a stable environment for life, shielded from the planet's potentially harsh surface conditions. Yet, the presence of a thick hydrogen envelope also complicates this picture. Hydrogen is an excellent greenhouse gas, meaning it could trap heat and create extreme temperatures on the surface, which might limit the habitability of the planet. These findings raise profound questions about what habitability truly means. For decades, scientists have used Earth as the benchmark for finding habitable planets, focusing on those that have similar sizes, atmospheres, and distances from their stars. However, K2-18b challenges this Earth-centered view. If life were to exist on a planet like K2-18b, it might not resemble anything we have ever seen before. Organisms could have evolved to thrive in conditions that would be lethal to life on Earth, much like extremophiles do in some of Earth's most inhospitable environments, such as hydrothermal vents or acidic lakes. The discovery of potential biosignatures on K2-18b is part of a broader trend in recent years that has revolutionized our understanding of the universe: the discovery of exoplanets. Since the first exoplanet was found in 1992, astronomers have confirmed the existence of over 5,000 exoplanets, and this number continues to grow as telescopes and detection methods improve. Each new exoplanet discovery broadens the scope of our search for life and teaches us more about the diversity of planets in the universe. However, detecting biosignatures on distant worlds is an exceedingly difficult task. The planets are too far away to be visited by spacecraft, and their faint signals are easily drowned out by the overwhelming light of their parent stars. The James Webb Space Telescope, launched in late 2021, is transforming this field by providing an unprecedented level of detail in its observations of distant planets. Equipped with state-of-the-art instruments capable of detecting the faintest infrared signals, the Webb telescope has given astronomers the ability to peer into the atmospheres of exoplanets like never before. It can measure the chemical compositions of these atmospheres, search for signs of clouds, weather systems, and even variations in temperature across the planet's surface. In the case of K2-18b, the telescope's observations have opened a new chapter in our quest to understand the potential for life elsewhere in the universe. The implications of these discoveries stretch far beyond K2-18b. If scientists can confirm that life exists, or once existed, on this distant world, it would represent one of the most profound paradigm shifts in human history. For centuries, humanity has wondered whether we are alone in the universe. The detection of life on another planet would not only answer this question, but also raise countless others. How widespread is life in the universe? Is it a rare phenomenon? Or is it common, flourishing wherever the conditions are right? Are there other forms of life, perhaps even intelligent life, waiting to be discovered elsewhere in the cosmos? These questions drive much of the current research in astronomy and astrobiology, and the answers may forever change our understanding of our place in the universe. In parallel with these developments, astronomers are also beginning to explore other tantalizing possibilities for habitability in our own solar system. Moons like Europa, which orbits Jupiter, and Enceladus, which orbits Saturn, have garnered significant attention in recent years due to evidence suggesting they may harbor subsurface oceans beneath their icy crusts. These moons are covered in ice, but beneath that ice, scientists believe there could be vast oceans of liquid water kept warm by tidal forces generated by the gravitational pull of their parent planets. On Enceladus, plumes of water vapor have even been observed erupting from cracks in the surface, offering a glimpse of the potentially life-sustaining ocean below. If life exists in these subsurface oceans, it could be similar to the microbial life forms found around hydrothermal vents on Earth, where organisms thrive in the absence of sunlight by using chemical energy from the Earth's interior. The search for life on these moons is still in its early stages, but several future missions aim to explore them in greater detail. NASA's upcoming Europa Clipper mission, set to launch in the mid-2020s, will conduct multiple flybys of Europa to study its ice shell, measure the thickness of its ocean, and assess the moon's potential for life. Similarly, the European Space Agency's JUICE, Jupiter Icy Moons Explorer, mission will focus on Ganymede, another of Jupiter's moons that may have a subsurface ocean. These missions could provide critical insights into the habitability of icy moons and the potential for life in environments vastly different from Earth. As astronomers continue to push the boundaries of our knowledge, they're also beginning to reconsider what exactly they are looking for when they search for signs of life. Traditionally, the search has focused on planets and moons with liquid water, oxygen, and other elements that are essential for life on Earth. However, some scientists now argue that life could exist in forms that do not rely on the same biochemistry as life on Earth. For example, it's possible that life could exist on planets or moons with environments that are too hot, too cold, or too acidic for Earth-based organisms to survive. This idea has led to a renewed interest in planets like Venus, which was long dismissed as too hostile for life due to its scorching surface temperatures and thick, sulfuric acid clouds. Recent observations, however, have raised the possibility that microbial life could exist in Venus's upper atmosphere, where temperatures and pressures are more moderate. The search for life in the universe is entering a new phase, one in which scientists are expanding the scope of their investigations and challenging long-held assumptions. Whether life exists elsewhere remains an open question, but with each new discovery, we are moving closer to an answer. K2-18b and other promising candidates like it offer us a glimpse into the possibilities that lie beyond our solar system, reminding us that the universe is far stranger and more diverse than we can imagine. Another fascinating aspect of recent astronomical discoveries is the detection of gravitational waves. These ripples in the fabric of space-time were predicted by Albert Einstein over a century ago as part of his theory of general relativity. But it wasn't until 2015 that they were directly observed for the first time. This groundbreaking discovery has opened an entirely new window into the universe, allowing scientists to observe events that would otherwise be invisible, such as the collision of black holes or the merging of neutron stars. Gravitational waves are produced by some of the most violent processes in the cosmos, such as supernovae or the collision of massive objects like black holes and neutron stars. When two black holes spiral closer together and eventually merge, they release a tremendous amount of energy in the form of gravitational waves. These waves travel through the universe at the speed of light, causing space-time itself to stretch and compress as they pass. Although the effect is incredibly small, distorting objects by less than the width of an atom, modern detectors like LIGO, Laser Interferometer Gravitational Wave Observatory, are sensitive enough to measure these minuscule changes. Since the first detection of gravitational waves in 2015, a number of significant discoveries have followed. One of the most notable was the observation of a neutron-star merger in 2017. Neutron stars are incredibly dense remnants of supernova explosions, and when two of them collide, they create a spectacular burst of gravitational waves, light, and electromagnetic radiation. This event, known as GW170817, was the first time that both gravitational waves and light were detected from the same cosmic event, ushering in a new era of multi-messenger astronomy. This type of astronomy allows scientists to study the same event through different forms of radiation, such as visible light, X-rays, and gamma rays, in addition to gravitational waves. The combination of these observations provides a more complete picture of the processes involved. In the case of GW170817, the merging neutron stars also produced heavy elements like gold and platinum, offering a new explanation for how these elements are formed in the universe. Previously, it was thought that supernovae were responsible for most of the heavy elements, but the discovery of this neutron-star merger has shown that these cosmic collisions also play a crucial role in the creation of such materials. The detection of gravitational waves is not only exciting for the new information it provides about the universe, but also because it has the potential to reveal entirely new types of cosmic phenomena. For instance, scientists are now searching for signals from primordial black holes, hypothetical objects that may have formed in the early universe. These black holes would have formed shortly after the Big Bang and could provide insights into the nature of dark matter, which makes up a significant portion of the universe's mass, but remains poorly understood. Moreover, gravitational waves are helping astronomers probe the very fabric of space-time itself. Some theories suggest that space-time might have a granular structure at incredibly small scales, far smaller than anything we can currently observe directly. Gravitational waves could offer a way to test these ideas by revealing tiny distortions in space-time as they pass through the universe. In this sense, the study of gravitational waves is not just about understanding the objects that produce them, but also about exploring the fundamental nature of the universe. Another exciting frontier in the study of gravitational waves is the search for signals from supermassive black hole mergers. While LIGO and similar detectors are well suited for detecting waves from smaller black holes and neutron stars, supermassive black hole mergers, such as those thought to occur when galaxies collide, produce lower frequency waves that are currently beyond the reach of ground-based detectors. To detect these waves, scientists are developing new techniques, including space-based observatories like the planned Laser Interferometer Space Antenna, LISA, which could detect signals from supermassive black holes millions of times the mass of the Sun. The implications of gravitational wave astronomy are profound. Not only does it allow us to observe events that are otherwise invisible, but it also provides a way to study the universe in a completely new way. In many ways, gravitational waves are like sound waves in the cosmic symphony, allowing us to hear the universe for the first time. As detectors become more sensitive and new observatories come online, the study of gravitational waves promises to revolutionize our understanding of the universe in ways we are only beginning to imagine. In addition to gravitational waves, another rapidly advancing field is the study of fast radio bursts, FRBs. These are incredibly brief, but powerful flashes of radio waves that originate from distant galaxies, lasting only a few milliseconds. Since their discovery in 2007, astronomers have been working to understand what causes these mysterious bursts. Unlike gravitational waves, which are predicted by general relativity, fast radio bursts were entirely unexpected, and their origin remains one of the biggest mysteries in modern astrophysics. One of the most intriguing aspects of fast radio bursts is their extreme energy. Despite lasting only a fraction of a second, each burst releases as much energy as the sun emits over several days. This immense energy, combined with the fact that the bursts seem to come from all directions in the sky, suggests that they are produced by powerful, distant cosmic events. Early theories propose that FRBs might be caused by cataclysmic events such as the collapse of massive stars, the merger of neutron stars, or even the evaporation of black holes. However, recent discoveries have complicated this picture. In 2020, astronomers observed an FRB originating from within our own galaxy, associated with a type of neutron star known as a magnetar. Magnetars are highly magnetized neutron stars that occasionally release bursts of energy, and this observation provided the first direct link between fast radio bursts and a known astrophysical object. While this discovery has helped narrow down the list of potential sources, it also suggests that there may be multiple types of FRBs with different origins, as most of the bursts observed so far have come from much more distant galaxies. Adding to the mystery, some FRBs are repeaters, meaning they emit multiple bursts over time from the same source, while others appear to be one-off events. This distinction has led to speculation that different types of fast radio bursts might have different causes. For instance, repeating FRBs could be produced by less violent processes, such as the interaction of a magnetar with its surrounding environment, while one-off FRBs might result from catastrophic events like neutron star collisions. The study of FRBs is still in its infancy, but new radio telescopes and observation techniques are rapidly expanding our knowledge of these enigmatic signals. The Canadian Hydrogen Intensity Mapping Experiment, CHIME, has been particularly successful in detecting fast radio bursts, discovering hundreds of new bursts, and helping to identify several repeating sources. As more bursts are observed, astronomers are starting to piece together a clearer picture of where they come from and what causes them. Despite these advances, fast radio bursts remain one of the biggest puzzles in astronomy. Their extreme energy, brief duration, and mysterious origins have led to speculation about the possibility of exotic explanations, including the idea that some FRBs could be signals from advanced alien civilizations. While this remains a fringe theory, the fact that fast radio bursts were completely unexpected serves as a reminder that the universe is full of surprises, and we may be on the verge of discovering entirely new types of cosmic phenomena. The study of gravitational waves and fast radio bursts exemplifies the way that astronomy is constantly evolving. As new technologies and techniques emerge, we are able to observe the universe in ways that were once thought impossible, revealing new mysteries and deepening our understanding of the cosmos. Whether it's detecting the ripples from a black hole merger or unraveling the source of a powerful radio burst from a distant galaxy, each new discovery brings us closer to answering some of the most fundamental questions about the nature of the universe. And yet, with each answer, new questions arise, reminding us that the cosmos is far more complex and mysterious than we can imagine. While the detection of gravitational waves and fast radio bursts have been capturing much of the attention in recent astronomical research, another area of exploration has started to gain momentum: the search for exomoons, moons that orbit planets outside our solar system. While the discovery of exoplanets has become almost routine, with over 5,000 confirmed exoplanets to date, the detection of moons around these planets remains far more elusive. Yet, if we find that moons are as common around exoplanets as they are around the planets in our solar system, it could significantly expand our understanding of planetary systems and their potential for harboring life. One of the key reasons exomoons are so intriguing is that they may offer new locations where life could potentially exist. Just as Europa and Enceladus, moons of Jupiter and Saturn respectively, are considered prime candidates for life in our solar system due to the subsurface oceans beneath their icy shells. Exomoons could provide similar environments in other star systems. In fact, some exomoons might even be more hospitable to life than their parent planets. For instance, a moon orbiting a gas giant in the habitable zone of its star might have a more stable climate than the planet itself, making it a better candidate for life. The search for exomoons, however, is technically challenging. Exoplanets are difficult enough to detect due to their relatively small size and faint signals compared to the stars they orbit. Detecting an exomoon, which would be even smaller and dimmer, is an even more delicate task. The methods used to find exoplanets, such as the transit method, where astronomers look for the dimming of a star's light as a planet passes in front of it, can in theory also be used to find exomoons. If a moon passes in front of a star, it should cause a slight additional dip in the star's brightness, or it might create tiny variations in the timing of the planet's transits, indicating the gravitational pull of a moon. One of the first and most compelling candidates for an exomoon is located in the Kepler 1625 system, about 8,000 light-years away. In 2018, astronomers using data from the Kepler Space Telescope announced the discovery of a large object orbiting the exoplanet Kepler 1625b, a gas giant several times the size of Jupiter. The object appears to be roughly the size of Neptune, making it far larger than any moon in our solar system. While the data suggests that this object could indeed be a moon, its unusually large size has raised questions about how it could have formed and whether it might actually be something else, such as a smaller planet in a binary orbit with Kepler 1625b. Despite the uncertainty surrounding this discovery, the potential existence of such a large exomoon is exciting because it challenges our understanding of how moons form. In our solar system, moons typically form through one of three mechanisms. They can form from the same material that makes up their parent planet, be captured by the planet's gravity, or result from massive impacts that eject material into orbit, such as the leading theory for the formation of Earth's moon. A Neptune-sized exomoon, however, would require a different explanation, possibly involving complex gravitational interactions between multiple planets in the system. As the search for exomoons continues, astronomers are refining their methods and looking for more subtle signals that could indicate the presence of smaller moons. Upcoming space telescopes like the James Webb Space Telescope, JWST, and the European Space Agency's Plato mission are expected to provide more detailed data that could help in the detection of exomoons. In particular, JWST's advanced infrared capabilities may allow scientists to directly observe exomoons by analyzing the heat they emit, which would be much fainter than the light from their parent planets or stars, but detectable with the right instruments. The discovery of exomoons would have profound implications not only for our understanding of planetary systems, but also for the potential habitability of these distant worlds. If moons are common around exoplanets, especially gas giants in the habitable zones of their stars, then the number of environments where life could potentially arise might be much larger than previously thought. Exomoons could have stable climates, liquid water, and atmospheres, making them prime candidates in the ongoing search for extraterrestrial life. In fact, some scientists argue that exomoons might be more favorable for life than exoplanets in certain cases. Large gas giants often have powerful magnetic fields that can protect their moons from harmful cosmic radiation. Additionally, tidal forces from the parent planet could generate internal heat in the moons, as is thought to happen on Europa and Enceladus, potentially sustaining liquid water beneath their surfaces even if they are far from their star's habitable zone. This line of thinking has led to the concept of a habitable moon or habitable satellite, a place where conditions are just right for life to thrive, even in systems that might otherwise seem inhospitable. In a sense, this expands the traditional concept of the habitable zone, the region around a star where conditions are suitable for liquid water, to include moons that might exist far outside this zone, but still have the necessary ingredients for life due to the influence of their parent planet. The detection of exomoons could also provide new insights into the formation and evolution of planetary systems. In our solar system, moons like Io, Europa, Ganymede, and Titan are thought to have formed in tandem with their parent planets or were captured by them at some point in the past. By studying exomoons, scientists can test these theories on a larger scale and see if similar processes occur in other star systems. This could help us understand how common Earth-like planets and moons are, and whether the conditions that led to the emergence of life on Earth are truly unique or part of a broader cosmic pattern. In the broader context of astronomy, the study of exomoons is just one part of a larger effort to understand the diversity of planetary systems in the universe. Since the discovery of the first exoplanet in 1992, we have learned that our solar system is just one of countless configurations of planets and moons that exist throughout the galaxy. Some systems contain planets with eccentric orbits that swing wildly close to and far from their stars, while others have tightly packed systems of planets orbiting much closer to their stars than Mercury does to the Sun. The diversity of these planetary systems raises intriguing questions about how common Earth-like conditions might be. While many of the exoplanets discovered so far are gas giants similar to Jupiter or Neptune, a growing number of smaller, rocky planets are being identified in the habitable zones of their stars. The search for life on these planets is one of the most exciting frontiers in modern astronomy, and the discovery of exomoons could significantly expand the number of potentially habitable worlds. As technology advances and our observational capabilities improve, we are likely to find more exomoons and learn more about their characteristics. Whether these moons are barren rocks or thriving environments with the potential for life, each new discovery will add to our understanding of the universe and our place within it. The hunt for exomoons is just beginning, but it promises to open up a whole new chapter in the story of planetary exploration. While the search for exomoons continues, another area that has garnered significant interest is the study of rogue planets, planets that do not orbit any star. These free-floating planets are thought to have been ejected from their parent planetary systems due to gravitational interactions, and they drift through the galaxy in the dark, far from the light and warmth of any star. Though they were once considered rare, recent evidence suggests that rogue planets may be more common than previously thought, with some estimates suggesting that they could even outnumber stars in the Milky Way. The discovery of rogue planets has profound implications for our understanding of planetary formation and the dynamics of planetary systems. It challenges the traditional view of planets as objects that form and remain in orbit around stars, showing that planets can be ejected from their systems and continue to exist in isolation. These lonely worlds could provide new insights into the processes that shape planetary systems and the forces that can tear them apart. Continuing the exploration of rogue planets, these mysterious free-floating worlds are unlike anything we've previously imagined in the structure of planetary systems. Without the gravitational pull of a star to anchor them, they wander through the vast emptiness of space, often in perpetual darkness. Recent studies have suggested that there could be billions of these planets in our galaxy alone, potentially even more than the number of stars. This staggering possibility raises intriguing questions about how rogue planets form and what kinds of environments might exist on these lonely, starless worlds. The origins of rogue planets are still a matter of debate. The most common hypothesis is that they were formed in a protoplanetary disk around a young star, much like the planets in our solar system, but were ejected due to gravitational interactions. These interactions could occur in the early stages of planetary system formation, when multiple large planets are jostling for position around their parent star. If one planet strays too close to another or interacts with a passing star, it could be flung out of the system entirely. Once free of its star's gravitational pull, the planet would become a rogue, drifting through space. Another possibility is that rogue planets could form independently of stars, directly from the collapse of a cloud of gas and dust, much like how stars themselves form. However, this process is thought to be much less common, as it would require specific conditions that are less likely to occur in isolation. Regardless of how they form, the discovery of rogue planets has profound implications for our understanding of planetary systems. It shows that planets can exist in environments very different from the ones we are familiar with, challenging our assumptions about what it means to be a planet. One of the most intriguing questions about rogue planets is whether they could potentially harbor life. At first glance, the idea of life existing on a planet without the warmth and light of a star might seem improbable. Without a star, there would be no source of energy to sustain life as we know it. However, scientists have pointed out that rogue planets could have alternative sources of heat that might make them more hospitable than they first appear. For example, rogue planets with thick atmospheres could retain heat from their formation for billions of years, creating environments that are warm enough for liquid water to exist beneath the surface. In addition, if these planets have significant geothermal activity, such as volcanic processes or radioactive decay, they could generate enough internal heat to sustain life in subsurface oceans, much like the icy moons of our solar system. This internal heating could create pockets of liquid water beneath a frozen surface, providing the essential conditions for life to arise and evolve. In our own solar system, moons like Europa and Enceladus provide a tantalizing glimpse of what might be possible on rogue planets. These moons are thought to have subsurface oceans heated by tidal forces generated by their parent planets. Even though these moons are far from the sun, this internal heating could make them habitable. A rogue planet with similar conditions could potentially have a stable, warm environment beneath its surface, even as it drifts through the cold darkness of interstellar space. One of the most promising ways to detect rogue planets is through a technique called gravitational microlensing. When a rogue planet passes in front of a distant star, its gravity acts like a lens, bending and magnifying the star's light. This effect can be observed from Earth, and by carefully analyzing the light curve, astronomers can infer the presence of the planet. Microlensing events are rare and brief, but they offer one of the best chances of detecting these elusive objects. In 2020, astronomers using the Optical Gravitational Lensing Experiment, OGLE, announced the discovery of a rogue planet with a mass similar to Earth, providing some of the best evidence yet that smaller, Earth-sized rogue planets exist in the galaxy. This discovery is significant because it suggests that rogue planets could come in a wide range of sizes, from gas giants like Jupiter to rocky worlds like Earth. The detection of an Earth-mass rogue planet raises the tantalizing possibility that some of these planets could have environments similar to those found on Earth, at least in terms of size and composition. The existence of rogue planets also complicates our understanding of the habitable zone, the region around a star where conditions are suitable for liquid water to exist on a planet's surface. Traditionally, the habitable zone is defined by the distance from a star where a planet's temperature would allow water to remain liquid. However, the discovery of potentially habitable rogue planets shows that a star may not be necessary for a planet to have liquid water, expanding the definition of what we consider to be a habitable world. In addition to the potential for life, rogue planets could also serve as natural laboratories for studying planetary evolution in extreme conditions. Without the influence of a parent star, rogue planets would be subjected to very different environmental pressures than planets that orbit stars. Studying these planets could provide new insights into how planetary atmospheres evolve, how internal heat sources interact with planetary surfaces, and how magnetic fields behave in the absence of a solar wind. Moreover, if rogue planets are as common as some studies suggest, they could offer a wealth of targets for future space missions. Although reaching a rogue planet would be an extraordinary challenge due to their isolation and the vast distances involved, new technologies such as nuclear-powered spacecraft or advanced propulsion systems might one day make it possible to explore these wandering worlds up close. Such missions could provide unprecedented insights into planetary formation, the potential for life in extreme environments, and the diversity of planetary systems in our galaxy. As our technology and understanding of the universe continue to improve, the study of rogue planets is likely to become a growing field of interest. With the potential to discover planets that defy our expectations and expand our understanding of habitability, rogue planets represent one of the most exciting frontiers in modern astronomy. They remind us that the universe is full of surprises and that our search for life and understanding of planetary systems must extend beyond the familiar and into the unknown. Beyond rogue planets, astronomers are also turning their attention to the mysterious dark matter that makes up a significant portion of the universe's mass. Although it cannot be seen directly, dark matter is thought to make up about 85% of the matter in the universe. and its presence can be inferred from its gravitational effects on galaxies and other large-scale structures. Despite decades of research, the true nature of dark matter remains one of the biggest unsolved mysteries in physics. One of the leading candidates for dark matter is a type of hypothetical particle known as a WIMP, weakly interacting massive particle. WIMPs would interact with normal matter only through gravity and the weak nuclear force, making them incredibly difficult to detect. However, ongoing experiments are attempting to capture the rare interactions between dark matter particles and ordinary matter using highly sensitive detectors placed deep underground, where they are shielded from cosmic rays and other sources of interference. In recent years, another potential candidate for dark matter has emerged: primordial black holes. These black holes would have formed shortly after the Big Bang, and their masses could range from tiny subatomic sizes to much larger objects. If primordial black holes exist, they could account for at least some of the dark matter in the universe. The search for these objects is ongoing, and if they are discovered, it could provide a revolutionary new understanding of both dark matter and the early universe. The study of dark matter and rogue planets, though seemingly unrelated, both highlight the vast and largely unknown aspects of the cosmos. These two fields challenge our understanding of the universe's composition and push the boundaries of our knowledge about how galaxies, planetary systems, and even the fundamental forces of nature operate. As astronomers and physicists continue to explore these frontiers, we are likely to uncover more surprises that reshape our understanding of the universe and our place within it. Another remarkable area of research that is reshaping our understanding of the cosmos is the study of exoplanet atmospheres. With recent advances in telescope technology and data analysis, astronomers are now able to examine the chemical compositions of atmospheres on distant planets, offering critical insights into their potential habitability, weather patterns, and even signs of alien life. The ability to sniff the atmospheres of exoplanets, as some researchers put it, has rapidly become one of the most exciting frontiers in astronomy. One of the major breakthroughs in this field came with the launch of the James Webb Space Telescope, JWST, which has provided unprecedented sensitivity and resolution for studying exoplanet atmospheres. The telescope is equipped with instruments capable of detecting the faintest traces of molecules like water vapor, methane, carbon dioxide, and oxygen, substances that can be key indicators of the planet's ability to support life. These molecules also reveal important information about the planet's climate, surface conditions, and even geological processes. Before JWST, the Hubble Space Telescope and other ground-based observatories laid the groundwork for this type of study. Using a technique called transmission spectroscopy, astronomers measure the starlight that passes through an exoplanet's atmosphere as the planet transits or passes in front of its host star. As the starlight filters through the planet's atmosphere, different molecules absorb specific wavelengths of light, leaving unique signatures or fingerprints in the spectrum that can be detected from Earth. This technique has already produced some striking discoveries. For example, astronomers have detected water vapor in the atmospheres of several exoplanets, including some super-Earths and hot Jupiters. Water is considered one of the essential ingredients for life as we know it, and its presence in exoplanet atmospheres is a strong indicator that liquid water could exist on the planet's surface, at least under the right conditions. More recently, the detection of water vapor in the atmosphere of K2-18b, a planet in the habitable zone of its star, made headlines because it raised the possibility of life-supporting environments on worlds much different from Earth. Methane is another molecule that has garnered significant attention in the search for life beyond Earth. On Earth, methane is produced by both geological processes and biological activity, making it a potential biosignature. However, detecting methane alone is not enough to confirm the existence of life, as non-biological processes, such as volcanic activity, can also produce methane. Therefore, astronomers look for other molecules, such as oxygen or carbon dioxide, in combination with methane to build a stronger case for biological activity. The presence of both methane and oxygen, for instance, would be particularly compelling, as these molecules would likely not coexist in large quantities unless some process, like life, was replenishing them. One of the most anticipated aspects of JWST's mission is its ability to analyze the atmospheres of Earth-sized exoplanets in the habitable zones of their stars. These planets, often referred to as temperate or Earth-like planets, orbit their stars at distances where temperatures are just right for liquid water to exist on the surface. If JWST or future missions can detect the right combination of gases in the atmospheres of these planets, such as water vapor, oxygen, methane, and carbon dioxide, it would be a major step toward identifying worlds that could potentially support life. However, the detection of biosignatures is only one part of the story. The study of exoplanet atmospheres is also helping astronomers understand the diversity of planets and their environments across the galaxy. Some of the first exoplanet atmospheres analyzed were those of hot Jupiters, gas giants that orbit extremely close to their stars. These planets are far too hot to support life as we know it, with temperatures often exceeding 1,000 degrees Celsius. But their thick atmospheres provide valuable data about how atmospheres evolve and interact with their parent stars. Hot Jupiters have some of the most extreme weather patterns in the universe. Astronomers have discovered that these planets often have high-speed winds, sometimes reaching speeds of several kilometers per second, that transport heat from the planet's day side, which is constantly facing its star, to its night side. In some cases, these winds may even drive rain made of molten rock or glass, depending on the planet's atmospheric composition. By studying these worlds, astronomers are learning more about the physics of atmospheric circulation and the complex dynamics that govern weather on planets far beyond our solar system. One particularly interesting discovery is the existence of super-puff planets, exoplanets that have a very low density, meaning they are large but incredibly lightweight for their size. These planets, which are often compared to cotton candy due to their low density, challenge our understanding of how planetary atmospheres work. Some superpuffs have atmospheres that are hundreds of times thicker than Earth's, raising questions about how such planets could have formed and what processes are keeping their atmospheres from escaping into space. Another major focus of exoplanet atmosphere research is the study of planets around M-dwarf stars, which are smaller and cooler than the Sun. M-dwarfs are the most common type of star in the galaxy, and many of the Earth-sized exoplanets detected to date orbit within the habitable zones of these stars. However, M-dwarfs are known for their frequent and intense stellar flares, which could strip away a planet's atmosphere and make it difficult for life to survive. By studying the atmospheres of exoplanets around M-dwarfs, astronomers hope to determine whether these planets can maintain stable, life-supporting environments despite the harsh radiation from their parent stars. One of the key challenges in studying exoplanet atmospheres is distinguishing between the different processes that can create similar atmospheric signatures. For instance, methane and oxygen could be produced by biological organisms, but they could also result from geological or chemical processes. To address this challenge, scientists are developing more sophisticated models of planetary atmospheres that take into account the planet's size, mass, temperature, and the type of star it orbits. These models help astronomers interpret the data from telescopes and determine whether the atmospheric signatures they are seeing are likely to be the result of life or some other process. Looking ahead, future missions like the European Space Agency's Aerial, Atmospheric Remote Sensing Infrared Exoplanet Large Survey, and NASA's HABEX, Habitable Exoplanet Observatory, are expected to build on the success of JWST and provide even more detailed observations of exoplanet atmospheres. Aerial, set to launch in the late 2020s, will focus on studying the atmospheres of a wide variety of exoplanets, from gas giants to Earth-like planets, using infrared spectroscopy. By observing hundreds of exoplanets across a broad range of conditions, Aerial will help scientists understand the diversity of planetary atmospheres and how they evolve over time. Meanwhile, HABEX, which is still in the conceptual phase, aims to directly image Earth-like exoplanets and analyze their atmospheres for signs of habitability. One of the key goals of HABEX is to search for biosignatures on nearby exoplanets, such as oxygen and methane, that could indicate the presence of life. If successful, this mission could provide the first concrete evidence of life beyond Earth, a discovery that would forever change our understanding of the universe and our place in it. The study of exoplanet atmospheres is still in its infancy, But the rapid pace of discoveries in recent years suggests that we are on the cusp of major breakthroughs. As new telescopes come online and our techniques for analyzing atmospheric data improve, we are likely to learn much more about the conditions on distant worlds, including whether any of them might harbor life. Whether it's detecting water vapor on a super-Earth, mapping the extreme weather on a hot Jupiter, or finding the first evidence of life on an exoplanet, the exploration of exoplanet atmospheres is one of the most exciting and promising areas of modern astronomy. Each new discovery brings us closer to answering the age-old question: are we alone in the universe? The study of exoplanet atmospheres is helping to reveal just how diverse and complex planetary systems can be, and with every new observation, we are reminded that the universe is far richer and more mysterious than we ever imagined. Whether through the detection of life, the understanding of planetary formation, or the unraveling of new physical processes, the exploration of these distant worlds will undoubtedly continue to push the boundaries of human knowledge and curiosity. As we delve deeper into the cosmos, one of the most tantalizing mysteries that continues to captivate astronomers is the existence and nature of dark energy. First discovered in the late 1990s, dark energy is a mysterious force that seems to be driving the accelerated expansion of the universe. Despite making up roughly 70% of the universe's total energy content, its true nature remains one of the greatest puzzles in cosmology. Understanding dark energy could unlock answers to fundamental questions about the fate of the universe, the behavior of gravity on the largest scales, and even the fundamental laws of physics themselves. The discovery of dark energy came as a complete surprise. For much of the 20th century, astronomers believed that the universe was expanding at a rate that should eventually slow down due to the gravitational pull of all the matter it contains. However, in the late 1990s, two independent teams of scientists studying distant supernovae, a type of exploding star, made a shocking discovery. The expansion of the universe wasn't slowing down at all. In fact, it was speeding up. This revelation led to the conclusion that some unknown force, which scientists now call dark energy, was counteracting gravity and causing the universe to expand at an ever-increasing rate. The most widely accepted explanation for dark energy comes from Einstein's theory of general relativity. Einstein introduced a term known as the cosmological constant to his equations of general relativity, which he later abandoned after realizing the universe was expanding, calling it his biggest blunder. However, with the discovery of dark energy, the cosmological constant made a comeback. This constant represents a fixed amount of energy that permeates all of space, causing the universe to expand. In this view, dark energy is simply the energy of empty space itself, a concept that aligns with certain aspects of quantum field theory, which suggests that even a perfect vacuum isn't truly empty, but filled with fluctuating energy. However, the cosmological constant explanation presents some serious challenges. One of the biggest issues is the vacuum catastrophe, which arises when physicists try to calculate the energy of empty space using quantum mechanics. Their calculations suggest that the amount of vacuum energy should be about 120 orders of magnitude larger than what is observed, an incomprehensibly large discrepancy. This problem has led some scientists to explore alternative explanations for dark energy. One such alternative is the concept of quintessence, a dynamic form of dark energy that changes over time, unlike the cosmological constant, which remains fixed. In this theory, dark energy is the result of a new type of scalar field, similar to the Higgs field, that pervades the universe. Unlike the static energy of the cosmological constant, quintessence would evolve as the universe expands, which could potentially explain why the effects of dark energy appear to have become dominant only in the relatively recent history of the universe. While quintessence offers an intriguing possibility, there is currently no direct evidence for such a field, and it remains a speculative hypothesis. Another possibility is that dark energy is a manifestation of a more profound modification of gravity itself. In this scenario, the acceleration of the universe's expansion might be the result of changes in the way gravity behaves on the largest cosmic scales. Some theories, such as modified gravity models, suggest that general relativity while highly successful in describing the behavior of gravity on smaller scales, such as within our solar system, may not be the full story when it comes to the dynamics of the entire universe. These models propose that gravity weakens at great distances, allowing dark energy to take over and drive the accelerated expansion. Testing these modified gravity theories requires extremely precise measurements of the universe's expansion rate and the distribution of matter on the largest scales. To unravel the mysteries of dark energy, astronomers are conducting increasingly detailed surveys of the universe. The Dark Energy Survey (DES), which began in 2013, is one of the largest efforts to study dark energy by mapping the positions and shapes of hundreds of millions of galaxies. By measuring how the distribution of galaxies changes over time, DES aims to better understand how the universe is expanding and how dark energy is affecting its large-scale structure. Another major initiative is the European Space Agency's Euclid mission, which is set to launch in the coming years. Euclid will map the shape, distribution, and evolution of galaxies and galaxy clusters over a large portion of the sky. By observing these cosmic structures at different stages in the universe's history, Euclid will provide crucial data on the effects of dark energy and test theories about its nature. NASA's Nancy Grace Roman Space Telescope, also expected to launch later this decade, will complement Euclid's observations by performing detailed measurements of supernovae and gravitational lensing, two key tools in probing the universe's expansion. Gravitational lensing, in particular, has become one of the most powerful techniques for studying dark energy. It occurs when the gravity of a massive object, such as a galaxy or cluster of galaxies, bends the light from more distant objects, creating distorted or magnified images. By measuring these distortions, astronomers can infer the amount and distribution of matter, both normal and dark, in the universe, as well as how this distribution has changed over time. Since dark energy affects the growth of cosmic structures, gravitational lensing provides a direct way to study its influence on the evolution of the universe. In addition to these observational efforts, theoretical physicists are exploring new ideas about the nature of dark energy. One of the most speculative but fascinating ideas is the possibility that dark energy could be a sign of the multiverse. According to this hypothesis, our universe is just one of many in a vast multiverse, each with its own physical laws and constants. In some of these universes, dark energy might be much stronger or weaker, or it might not exist at all. The fact that our universe has a small, but non-zero, amount of dark energy could be a result of cosmic selection. Only universes with a small amount of dark energy would allow galaxies, stars, and planets to form, making them the only universes where life could exist to observe them. While the multiverse idea is highly speculative and controversial, it illustrates how the search for dark energy is pushing the boundaries of both physics and philosophy. Understanding dark energy may require not just new observations of the universe, but also a deeper understanding of the fundamental nature of reality itself. It forces us to confront questions about the ultimate fate of the universe, whether the laws of physics we observe are unique to our universe or part of a broader set of possibilities, and whether the universe will continue to expand forever or eventually collapse in on itself. If dark energy continues to drive the accelerated expansion of the universe, it could lead to a scenario known as the Big Freeze. In this future, galaxies would continue to drift farther and farther apart, eventually becoming isolated from each other. Over trillions of years, stars would burn out, black holes would evaporate, and the universe would grow cold and dark as all matter and energy are spread thin across an ever-expanding void. Alternatively, if dark energy were to change over time, perhaps as predicted by quintessence models, the universe could experience a big crunch, in which the expansion eventually reverses and the universe collapses in on itself. There is also the more exotic possibility of a big rip, where dark energy grows stronger over time, eventually tearing apart galaxies, stars, planets, and even atoms themselves. In this scenario, the universe's expansion would accelerate to such an extreme that all structures would be ripped apart by the relentless force of dark energy. These scenarios, while speculative, highlight the profound implications of understanding dark energy. It is not just a matter of understanding the current state of the universe, but of predicting its ultimate fate. The discovery of dark energy has revolutionized cosmology, and as we continue to study it, we are likely to uncover even deeper mysteries about the nature of the universe and the forces that shape it. As we push the boundaries of knowledge in our quest to understand dark energy, we are reminded of the vastness of the universe and the complexity of the forces at play. The study of dark energy, like so many other areas of astronomy, invites us to confront the limits of our understanding and to ponder the most profound questions about existence itself. What is dark energy? Why does it exist? And what does it mean for the future of the cosmos? These are questions that continue to drive astronomers and physicists alike as they seek to unlock the secrets of the universe and our place within it. As we continue to explore the cosmos, one of the most exciting and mysterious areas of research is the study of black holes. Those enigmatic objects whose gravity is so intense that not even light can escape their pull. Black holes have long been a subject of fascination and speculation, but recent discoveries and advances in technology are providing us with unprecedented insights into their nature, behavior, and role in the universe. From the detection of black hole mergers via gravitational waves to the first-ever image of a black hole's event horizon, the study of these cosmic giants is entering a new era, offering answers to some of the deepest questions in astrophysics while raising new ones. Black holes are formed when massive stars collapse at the end of their life cycles, compressing all of their mass into an extremely small and dense point called a singularity. Surrounding this singularity is the event horizon, the boundary beyond which nothing, not even light, can escape. For decades, black holes were primarily theoretical objects, predicted by Einstein's theory of general relativity. But over the past few decades, astronomers have gathered mounting evidence that black holes not only exist but play a crucial role in the evolution of galaxies and the universe itself. One of the most significant breakthroughs in black hole research came in April 2019, when scientists from the Event Horizon Telescope, EHT, collaboration released the first-ever image of a black hole. This image showed the supermassive black hole at the center of the galaxy M87, a monstrous object with a mass 6.5 billion times that of the Sun. The image, which revealed the black hole's shadow against a glowing ring of hot gas, was a monumental achievement in both observational astronomy and the study of general relativity. It provided the most direct evidence yet of the existence of event horizons and confirmed many of the predictions made by Einstein's theory about how light and matter behave around black holes. The Event Horizon Telescope achieved this feat by linking together radio telescopes across the globe, effectively creating a planet-sized telescope that was able to capture the incredibly faint and distant light signals from the region around the black hole. By combining data from multiple observatories and using advanced algorithms to process the signals, the EHT team was able to reconstruct the image of the black hole's shadow. This breakthrough opened a new chapter in the study of black holes, allowing scientists to test fundamental theories of gravity and the behavior of matter in extreme environments. The success of the EHT was followed by another milestone in 2022, when the team released an image of Sagittarius A*, the supermassive black hole at the center of our own galaxy, the Milky Way. Although much smaller than M87's black hole, with a mass about 4 million times that of the Sun, Sagittarius A* is of particular interest because of its proximity, just 26,000 light-years away, making it one of the best laboratories for studying the physics of black holes. The image of Sagittarius A* provided further confirmation of the strange and powerful effects that black holes exert on their surroundings, from the warping of space-time to the heating of nearby gas to millions of degrees. While images of black holes have captured the public imagination, another major area of black hole research has focused on their mergers and the gravitational waves they produce. When two black holes orbit each other and eventually merge, they release an immense amount of energy in the form of gravitational waves, ripples in space-time that propagate across the universe. The detection of these waves was first accomplished by the LIGO, Laser Interferometer Gravitational Wave Observatory, and Virgo collaborations in 2015, a discovery that earned the 2017 Nobel Prize in Physics. Since then, gravitational wave observatories have detected dozens of black hole mergers, providing a new way to study these otherwise invisible objects. Each detection offers valuable data about the masses, spins, and distances of the merging black holes, as well as clues about how and where they formed. For example, some black hole mergers involve surprisingly massive black holes, far larger than what scientists had predicted based on known stellar evolution models. These discoveries have prompted new questions about the environments in which such black holes form, perhaps in dense star clusters or in the disks of supermassive black holes at the centers of galaxies. One particularly intriguing discovery was the detection of a merger involving an intermediate mass black hole with a mass about 150 times that of the Sun. This was the first direct evidence of the existence of black holes in this mass range, which had long been hypothesized but had never been observed. Most known black holes fall into two categories: stellar mass black holes, which form from collapsing stars and typically have masses between a few and several tens of times that of the Sun, and supermassive black holes, which sit at the centers of galaxies and have masses ranging from millions to billions of times that of the Sun. Intermediate mass black holes, which are thought to bridge the gap between these two populations, remain poorly understood, and their discovery through gravitational wave detections has opened a new avenue for understanding how black holes grow and evolve. Another area of black hole research that is gaining traction is the study of black hole jets, powerful streams of energy and particles that are ejected from the regions around black holes at nearly the speed of light. These jets are typically associated with supermassive black holes in active galactic nuclei, AGN, where they can extend across vast distances, sometimes spanning entire galaxies. The mechanisms behind the formation of these jets are still not fully understood, but they are thought to arise from the interaction between the black hole's magnetic field and the swirling disk of gas and dust that surrounds it. Studying black hole jets not only helps scientists understand how black holes influence their surroundings, but also provides insights into the behavior of matter in extreme conditions and the role black holes play in shaping galaxy formation. In recent years, observations from high-energy observatories like NASA's Chandra X-ray Observatory and the European Space Agency's XMM Newton have provided detailed images of these jets, revealing complex structures and interactions between the jets and the interstellar medium. These observations show that black hole jets can have a profound impact on their host galaxies, sometimes driving out gas and preventing star formation in a process known as feedback. This feedback mechanism is thought to play a critical role in the evolution of galaxies, helping to explain why many massive galaxies contain little gas and no longer form stars despite the presence of abundant material that could otherwise collapse to form new stars. In addition to their astrophysical importance, black holes are also a key focus in the search for a unified theory of quantum gravity, a theory that would reconcile the two pillars of modern physics: general relativity, which describes gravity on large scales, and quantum mechanics, which governs the behavior of particles on the smallest scales. Black holes represent the ultimate test for such a theory because they embody both extreme gravitational fields and quantum effects. The famous information paradox, for example, arises from the apparent contradiction between general relativity and quantum mechanics regarding what happens to information that falls into a black hole. According to general relativity, anything that crosses a black hole's event horizon is lost forever, along with the information about its physical state. However, this clashes with a fundamental principle of quantum mechanics, which states that information cannot be destroyed. This paradox has led to intense debates among physicists and has spurred the development of new theories, including the idea of holography and the firewall hypothesis, both of which attempt to resolve the conflict between gravity and quantum theory. One of the most promising frameworks for addressing the black hole information paradox comes from string theory, which suggests that the information might be encoded on the event horizon itself, much like a hologram. This idea is closely related to the broader concept of the holographic principle, which posits that the entire universe can be described as a two-dimensional surface that encodes all the information within it. While these ideas remain speculative, they represent cutting-edge attempts to unify our understanding of gravity and quantum mechanics, and black holes provide the perfect laboratory for testing these theories. As technology improves and our ability to observe black holes advances, the future of black hole research holds even more exciting possibilities. Planned space-based gravitational wave observatories like the Laser Interferometer Space Antenna, LISA, will allow us to detect gravitational waves from supermassive black hole mergers and probe black hole environments that are currently beyond our reach. These observations will help answer some of the most fundamental questions about black holes. How do they grow? How do they interact with their surroundings? And what role do they play in the evolution of the universe? At the same time, theoretical advances in quantum gravity and the study of black hole thermodynamics could bring us closer to resolving the deep mysteries surrounding black holes and their connection to the fundamental forces of nature. As we explore these questions, black holes continue to offer a profound glimpse into the nature of the universe, acting as cosmic laboratories for understanding some of the most extreme phenomena in existence. The study of black holes not only reveals the power and complexity of the universe, but also challenges us to rethink our understanding of space, time, and the very fabric of reality itself. As we push forward in our exploration of these enigmatic objects, we are reminded that while black holes may represent the end for matter and energy that falls into them, they're also the beginning of new realms of discovery for humanity's quest to understand the cosmos. In the ever-evolving journey to understand the universe, one of the most intriguing and recent areas of exploration is the study of planetary migration, particularly in relation to how planets, especially giant gas planets like Jupiter, move within their solar systems over time. This research is changing our understanding of planetary formation and the early dynamics of our own solar system, while also offering insight into the thousands of exoplanetary systems we've discovered. The discovery that planets can shift significantly from their original orbits has upended previous assumptions that planetary systems are static once formed, revealing a dynamic and chaotic process that can dramatically reshape the architecture of entire solar systems. Planetary migration refers to the phenomenon where a planet moves from its initial orbit, often much closer or farther from its parent star than it was when it first formed. The discovery of hot Jupiters, giant gas planets like Jupiter, but orbiting extremely close to their stars, was one of the first clues that planetary migration might be common. According to traditional models of planetary formation, gas giants like Jupiter should form far from their stars, where it's cold enough for volatile compounds like water and methane to condense and help build up a large planet. The presence of these massive planets so close to their stars, where temperatures can reach thousands of degrees, was a clear sign that they must have formed farther out and migrated inward over time. This realization sparked a wave of research into the mechanisms that drive planetary migration. One of the most widely accepted explanations involves the interaction between young planets and the protoplanetary disks of gas and dust from which they form. As a planet orbits within this disk, its gravity causes waves to form in the surrounding material. These waves exert a gravitational pull on the planet, which can cause it to lose angular momentum and spiral inward toward the star or, in some cases, outward away from the star. This process is known as disk-driven migration, and it is thought to be responsible for many of the hot Jupiters and other close-in giant planets that astronomers have detected. However, disk-driven migration is not the only way planets can move. Another significant process is planet-planet interactions. Early in a solar system's history, before the planets settle into stable orbits, gravitational interactions between multiple planets can lead to dramatic changes in their orbits. These interactions can result in planets being ejected from the system entirely, thrown into highly eccentric orbits, or pushed into much closer or farther orbits than where they originally formed. In some cases, these interactions can even lead to collisions between planets or with other objects in the system, further shaping the final arrangement of the planetary orbits. Our own solar system provides compelling evidence that planetary migration has played a significant role in shaping the arrangement of the planets we see today. One of the most important models of solar system evolution, known as the Nice model, named after the city in France where it was developed, suggests that Jupiter and Saturn may have migrated significantly after they formed. According to this model, Jupiter may have initially moved inward before interacting with Saturn and other giant planets, which caused it to reverse course and migrate outward. This outward migration is believed to have had profound effects on the entire solar system, scattering smaller bodies in the outer regions and possibly triggering the late heavy bombardment, a period of intense asteroid and comet impacts that struck the inner planets, including Earth about 4 billion years ago. The idea that Jupiter migrated early in the solar system's history also helps explain the current arrangement of the asteroid belt, which lies between the orbits of Mars and Jupiter. Early in its formation, the asteroid belt may have contained much more material, including many more planetesimals, small bodies that can eventually grow into planets. However, as Jupiter moved through this region, its immense gravity would have stirred up the material, preventing most of it from coalescing into a planet and scattering much of it either inward toward the Sun or outward into the Kuiper Belt, a distant region of icy bodies beyond Neptune. This process explains why the asteroid belt today contains only a small fraction of the material needed to form a planet, despite its vast size. Planetary migration also offers insights into why the outer regions of our solar system are populated with objects like Pluto, Eris, and other distant dwarf planets in the Kuiper Belt, and the even more remote Oort cloud. As the giant planets migrated, their gravity likely scattered many icy bodies outward into these distant regions. Some of these objects were ejected from the solar system entirely, while others settled into stable orbits far from the Sun. This outward scattering process also provides an explanation for the highly elongated orbits of some trans-Neptunian objects, whose trajectories suggest they were disturbed by the gravitational influence of the giant planets early in the solar system's history. The study of exoplanetary systems has further reinforced the idea that planetary migration is a common feature of planetary evolution. Observations of exoplanets have revealed a wide variety of planetary arrangements, many of which are very different from our solar system. In some systems, planets much larger than Earth orbit extremely close to their stars, while in others, massive gas giants are found in highly eccentric orbits. These findings suggest that the processes of migration and gravitational interactions that we see in our own solar system are likely to be even more chaotic and complex in other star systems, leading to a much wider diversity of planetary configurations than previously thought. One particularly interesting discovery is that of systems with multiple planets locked in orbital resonances, where the planets' orbits are in a precise ratio with each other. For example, one planet might orbit the star exactly twice for every orbit of another planet. These resonances can be strong indicators of past planetary migration, as planets that migrate through a disk of gas and dust can become trapped in these resonant configurations, locking them into stable orbits that persist for billions of years. The TRAPPIST-1 system, a nearby system of 7 Earth-sized planets, is a well-known example of a system with multiple planets in resonance, and studying such systems can provide important clues about the early stages of planetary migration. One of the most compelling consequences of planetary migration is its potential impact on the habitability of planets and moons. As planets migrate, they can move in and out of the so-called habitable zone, the region around a star where temperatures are just right for liquid water to exist on a planet's surface. A planet that forms outside the habitable zone might migrate inward and become warm enough to support life, while a planet that forms within the habitable zone could be pushed out into colder regions where liquid water cannot exist. This means that the potential for life in a planetary system could change dramatically over time as planets migrate. In addition, planetary migration could influence the habitability of moons. Gas giants like Jupiter and Saturn, which are common in both our solar system and in many exoplanetary systems, often have large moons that could potentially harbor life. If these gas giants migrate, their moons are carried along with them, potentially bringing them into habitable zones where conditions could be favorable for life to develop. The icy moons of Jupiter and Saturn, such as Europa and Enceladus, are of particular interest because they are thought to have subsurface oceans that could support microbial life. If these moons were once closer to the Sun, they might have been even more habitable in the past. The potential for planetary migration to affect habitability also raises questions about how common life might be in the universe. If migration is a widespread phenomenon, It could mean that planets and moons with the right conditions for life are more common than previously thought, as planets can move into more favorable positions over time. On the other hand, migration could also disrupt potentially habitable planets, either by moving them out of the habitable zone or by causing gravitational interactions that destabilize their orbits. Looking ahead, new telescopes and observational techniques are poised to provide even more insights into planetary migration and its effects on planetary systems. Missions like NASA's James Webb Space Telescope, JWST, and the European Space Agency's Plato mission will be able to study the atmospheres and compositions of exoplanets in unprecedented detail, offering clues about their formation and migration histories. In addition, upcoming surveys of the outer regions of our solar system, such as the Vera C. Rubin Observatory's Legacy Survey of Space and Time, LSST, will provide new data on the distant objects scattered by planetary migration, helping us piece together the early history of our own solar system. As our understanding of planetary migration grows, it is becoming clear that this process is a fundamental aspect of planetary formation and evolution. Planets are not static objects locked into place from the moment they form. Rather, they're dynamic entities that can move, interact, and reshape their environments over billions of years. This realization has profound implications for our understanding of how solar systems form, how planets evolve, and where we might find life in the universe. As we continue to study this phenomenon, we are likely to uncover even more surprises about the chaotic and ever-changing nature of planetary systems, both in our solar system and beyond. As we push further into the frontiers of space exploration, one of the most exciting and transformative areas of research is the study of the moons of our outer solar system, particularly the icy moons of Jupiter and Saturn. These moons, Europa, Enceladus, Ganymede, and Titan, among others, have become prime targets in the search for extraterrestrial life. What makes these icy worlds so intriguing is the growing evidence that beneath their frozen exteriors lie vast oceans of liquid water, kept warm by geothermal processes. The possibility that these subsurface oceans could harbor life has sparked a new wave of missions and scientific inquiry, marking a shift in our understanding of where life might exist in the cosmos. For much of human history, the search for life beyond Earth focused primarily on planets with surface environments similar to our own. Mars, with its evidence of ancient rivers and lakes, has long been at the forefront of this search. However, discoveries over the past few decades have shifted the focus toward these icy moons, which may offer more favorable conditions for life in some ways than even Mars. The key reason is the potential for liquid water, a fundamental requirement for life as we know it, hidden beneath thick layers of ice. Europa, one of Jupiter's 4 largest moons, has emerged as one of the most promising candidates for life. First observed in detail by the Galileo spacecraft in the 1990s, Europa's surface is a chaotic landscape of ice, marked by cracks, ridges, and dark streaks that suggest the presence of a subsurface ocean. The surface itself is relatively young, geologically speaking, with few impact craters, indicating that the ice is being continually resurfaced by material rising from below. Scientists believe that Europa's ocean lies beneath an ice shell that could be several kilometers thick, and that this ocean could be up to 100 kilometers deep, much deeper than any ocean on Earth. What makes Europa particularly compelling is the potential for geothermal activity on the seafloor of its subsurface ocean, similar to the hydrothermal vents found on Earth's ocean floors, which teem with life despite the absence of sunlight. These vents could provide the energy and chemical nutrients needed to support microbial life. On Earth, life forms around hydrothermal vents rely on chemosynthesis, a process where organisms derive energy from the chemical reactions between minerals and the surrounding water, rather than from sunlight. If similar conditions exist on Europa, it raises the possibility that life could have evolved there independently, using entirely different processes from those on Earth. The evidence for a subsurface ocean on Europa was further bolstered by the discovery of water vapor plumes erupting from its surface. These plumes were first detected by the Hubble Space Telescope in 2012, and subsequent observations have confirmed their existence. The presence of these plumes suggests that water from the ocean beneath is making its way to the surface, providing a potential way for future missions to sample the ocean without having to drill through the thick ice shell. If scientists can capture and analyze the material from these plumes, they could search for signs of biological activity, such as organic molecules or other biomarkers that indicate the presence of life. NASA's upcoming Europa Clipper mission, set to launch in the 2020s, will take a closer look at this intriguing moon. Equipped with advanced instruments designed to study Europa's surface and subsurface in unprecedented detail, Europa Clipper will perform dozens of flybys of the moon, mapping its ice shell, searching for more water vapor plumes, and gathering data that could help determine whether its ocean is habitable. While the mission won't land on Europa, it will provide critical information that could pave the way for future landers or probes designed to explore the surface or sample the plumes directly. Another icy moon that has captured the attention of astrobiologists is Enceladus, one of Saturn's smaller moons. Like Europa, Enceladus is believed to harbor a global subsurface ocean beneath its icy shell, and it too has been observed ejecting water vapor and ice particles into space. In fact, the plumes of Enceladus, first discovered by NASA's Cassini spacecraft in 2005, have been one of the most compelling pieces of evidence in the search for life beyond Earth. Cassini's close flybys of Enceladus allowed scientists to analyze the composition of these plumes in detail, revealing not only water vapor, but also organic compounds, hydrogen, carbon dioxide, and salts, key ingredients for life. The detection of molecular hydrogen was particularly significant, as it suggests the presence of hydrothermal activity on Enceladus' ocean floor, much like the hydrothermal vents on Earth. These vents could provide the energy needed to sustain microbial life, making Enceladus one of the most exciting targets for future exploration. The discovery of these ingredients for life in Enceladus plumes has led to a surge of interest in sending a dedicated mission to this small but potentially life-bearing moon. Various mission concepts have been proposed, including the Enceladus Life Finder and the Orbalander mission, which would either fly through the plumes again or land on the moon's surface to search for direct signs of life. Unlike Mars, where evidence of life may be fossilized or extremely difficult to detect, the plumes of Enceladus offer a unique opportunity to sample fresh material from a subsurface ocean that could be teeming with life today. While Europa and Enceladus have garnered much of the attention in the search for life, they are not the only icy moons of interest. Ganymede, another of Jupiter's largest moons, is also believed to harbor a subsurface ocean. Ganymede is unique in that it is the largest moon in the solar system and the only moon known to have a magnetic field, which could help protect its ocean from harmful cosmic radiation. The European Space Agency's JUICE, Jupiter Icy Moons Explorer, mission, set to launch in the 2020s, will investigate Ganymede along with Europa and Callisto, providing valuable data on the conditions beneath their icy surfaces. Titan, Saturn's largest moon, presents an entirely different type of environment that could support life, albeit one that is radically different from life as we know it. Titan is the only moon in the solar system with a thick atmosphere, rich in nitrogen and hydrocarbons, and its surface is covered with lakes and seas of liquid methane and ethane. The Huygens probe, part of the Cassini mission, landed on Titan in 2005, revealing a landscape eerily similar to Earth's, with rivers, lakes, and even rain, except that the water on Titan is composed of hydrocarbons, and the surface temperature is a frigid minus 179 degrees Celsius. While Titan's surface is too cold for liquid water, scientists speculate that life could exist either in the methane lakes or, more likely, in a subsurface ocean of liquid water mixed with ammonia beneath the ice. If life exists on Titan, it would have to be based on completely different biochemistry than the carbon-based life on Earth, possibly using methane or other hydrocarbons as solvents instead of water. This makes Titan a fascinating target in the search for alternative forms of life. NASA's Dragonfly mission, set to launch in the mid-2020s, will send a rotorcraft to Titan's surface to explore its diverse environments, including its dunes, lakes, and possible cryovolcanoes, in search of organic compounds and other signs of prebiotic chemistry. The exploration of these icy moons is not just about the search for life. It also holds the potential to revolutionize our understanding of planetary processes, ocean worlds, and the conditions under which life can arise. These moons, with their hidden oceans and potential for life, challenge our traditional views of habitability, expanding the definition of the habitable zone beyond the immediate vicinity of stars to include the distant, frozen regions of the outer solar system. Moreover, the study of these moons has broader implications for our understanding of exoplanets and the potential for life in other solar systems. Many of the exoplanets discovered to date are gas giants similar to Jupiter and Saturn, and it's likely that some of these planets also have icy moons with subsurface oceans. If life can exist on Europa or Enceladus, it raises the possibility that similar moons around distant exoplanets could also harbor life, greatly expanding the number of potential life-bearing worlds in the universe. As missions to explore these icy moons continue, we are on the verge of uncovering some of the most profound answers about the nature of life in the universe. Whether we find signs of microbial life in the oceans of Europa or Enceladus, or discover entirely new forms of life on Titan, the exploration of these moons promises to reshape our understanding of biology, chemistry, and the conditions under which life can thrive. These frozen worlds, once considered barren and lifeless, may hold the keys to answering one of humanity's oldest and most profound questions. Are we alone in the universe? As we continue to unravel the secrets of our solar system, another frontier of exploration beckons with profound questions about both the origins of life and the very nature of planetary formation. The study of comets and asteroids. These small, often overlooked celestial bodies are far more than just remnants of cosmic debris. They are time capsules containing some of the oldest material from the formation of the solar system. Comets and asteroids may hold the key to understanding how planets formed, how water and organic molecules arrived on Earth, and whether the ingredients for life could have been seeded throughout the solar system and beyond by these wandering objects. The significance of comets and asteroids lies in their primordial nature. Unlike planets and moons, which have undergone significant geological changes over billions of years, comets and asteroids are thought to have remained largely unchanged since they first coalesced from the protoplanetary disk that surrounded the young sun. This makes them invaluable to scientists studying the early solar system. By examining the composition of these objects, researchers can gain insights into the processes that shape the formation of planets, as well as the delivery of water and organic compounds to Earth, a process that may have been essential for the emergence of life. Comets, often referred to as dirty snowballs, are composed of ice, dust, and rocky material. They typically originate in the distant reaches of the solar system, either in the Kuiper Belt, beyond Neptune, or in the even more distant Oort cloud. When a comet's orbit brings it close to the sun, the heat causes its ices to vaporize, creating the spectacular glowing coma and tail that comets are known for. This outgassing not only makes comets visible from Earth, but also releases materials from the comet's interior, providing a rare opportunity for scientists to study the composition of pristine solar system material. One of the most groundbreaking missions in the study of comets was the European Space Agency's Rosetta mission, which made history in 2014 when it became the first spacecraft to rendezvous with a comet, Comet 67P/Churyumov-Gerasimenko. Over the course of its mission, Rosetta captured unprecedented close-up images and data, revealing a wealth of information about the comet's surface, its composition, and the processes driving its activity. Rosetta's lander, Philae, also made the first-ever landing on a comet's surface, although its mission was cut short due to landing in a shaded area where its solar panels couldn't generate power. Still, the data gathered by Philae and Rosetta transformed our understanding of comets. Rosetta's observations provided several surprises. For one, Comet 67P was found to contain complex organic molecules, including amino acids, some of the building blocks of life. This discovery supported the hypothesis that comets may have played a crucial role in delivering organic compounds to the early Earth, possibly kickstarting the chemical processes that led to the development of life. Moreover, the water on Comet 67P was found to have a different isotopic composition than the water on Earth, suggesting that comets like 67P may not have been the primary source of Earth's oceans. This finding has prompted further investigations into whether asteroids, rather than comets, may have been the primary carriers of water to Earth. Asteroids, which are rocky rather than icy like comets, have also emerged as critical targets in the study of the solar system's history. Asteroids are primarily found in the asteroid belt between Mars and Jupiter, a region where planet formation was likely interrupted by the gravitational influence of Jupiter. These objects vary widely in size, shape, and composition, from small, metal-rich asteroids to large, rubble pile structures held together by gravity. Like comets, asteroids are thought to preserve material from the early solar system, offering clues about the conditions under which the planets formed. One of the most ambitious missions to study asteroids is NASA's OSIRIS-REx mission, which visited the near-Earth asteroid Bennu and successfully collected samples from its surface. Bennu is a carbon-rich asteroid, meaning it contains organic molecules that could shed light on the origins of life. In 2020, OSIRIS-REx touched down on Bennu's surface, using a robotic arm to collect samples that will be returned to Earth in 2023. These samples are expected to provide unprecedented insights into the composition of early solar system material, including organic compounds and possibly even prebiotic molecules. Another exciting asteroid mission is Japan's Hayabusa 2, which visited the asteroid Ryugu and, like OSIRIS-REx, returned samples to Earth. Ryugu, like Bennu, is a carbonaceous asteroid, and the analysis of its samples is expected to help scientists understand the distribution of organic molecules and water in the early solar system. These sample return missions represent a major leap forward in planetary science, as they allow researchers to analyze asteroid material in terrestrial laboratories with far greater precision than is possible with remote spacecraft observations. The study of asteroids has also taken on new significance due to their potential role in planetary defense. Near-Earth objects, NEOs, asteroids and comets that come close to Earth's orbit, pose a collision risk, albeit a small one. While large impacts like the one that likely caused the extinction of the dinosaurs are extremely rare, even smaller impacts could have devastating effects on human populations. In response, space agencies around the world have been developing strategies to detect, track, and if necessary, deflect dangerous asteroids. NASA's Double Asteroid Redirection Test (DART) mission, launched in 2021, aims to demonstrate a technique for altering an asteroid's trajectory by crashing a spacecraft into it. If successful, this technique could one day be used to prevent a potentially catastrophic impact. Beyond their potential to threaten Earth, asteroids are also seen as potential resources for future space exploration. Many asteroids contain valuable metals like iron, nickel, and platinum, and some space entrepreneurs envision a future where asteroid mining could supply raw materials for space construction and support human settlements on the Moon or Mars. In this vision, asteroids would become stepping stones for humanity's expansion into the solar system, providing the resources needed to build space habitats and fuel spacecraft without the need to launch everything from Earth. But perhaps the most intriguing aspect of comets and asteroids is their potential role in the delivery of life's ingredients. The idea that comets and asteroids could have delivered water and organic molecules to the early Earth is part of a broader hypothesis known as panspermia. According to this hypothesis, life, or at least the basic building blocks of life, could have originated in space and been transported to Earth by comets, asteroids, or even interstellar dust. While panspermia remains speculative, the discovery of organic molecules on comets like 67P and asteroids like Bennu lend support to the idea that the ingredients for life are widespread in the solar system and perhaps the universe. If this is true, it raises profound questions about the origin of life and the potential for life beyond Earth. Could life have arisen independently on multiple worlds in our solar system, seeded by comets and asteroids? Or could life on Earth itself be part of a cosmic chain, with the seeds of life traveling between star systems over billions of years? These questions push the boundaries of astrobiology and force us to reconsider our place in the cosmos. As technology improves, future missions will likely continue to explore comets, asteroids, and other small bodies in the solar system. Missions like NASA's proposed Comet Astrobiology Exploration Sample Return (CESAR) aim to bring back samples from comets, while ongoing studies of NEOs will help us better understand the risks and opportunities posed by these wandering objects. Meanwhile, the discovery of interstellar objects such as the mysterious Oumuamua, which passed through the solar system in 2017, suggests that comets and asteroids from other star systems could be reaching us as well, opening up entirely new avenues of exploration. As we continue to study these ancient objects, the story of comets and asteroids promises to reveal more about the solar system's earliest history, the origins of life, and the future of humanity in space. Far from being mere cosmic debris, these small bodies are at the center of some of the most important scientific questions we face, offering a window into both the past and the future of our solar system and potentially the universe at large. As we venture further into the mysteries of the cosmos, one of the most fascinating areas of exploration is the study of interstellar objects, those rare, fleeting visitors from outside our solar system. These objects, which traverse vast distances between the stars, offer us a glimpse of material and processes that lie far beyond our immediate cosmic neighborhood. The study of interstellar objects is a relatively new field, but it holds immense potential for advancing our understanding of planetary formation, the conditions in distant star systems, and the possibility of life in the universe. The discovery that sparked intense interest in interstellar objects came in 2017, when astronomers detected the first known interstellar visitor to our solar system, an object called 1I/Oumuamua. Its name, which means scout or messenger in Hawaiian, was fitting for this enigmatic traveler, as Oumuamua represented the first known physical object from another star system to pass through our own. Detected by the Pan-STARRS telescope in Hawaii, Oumuamua's highly unusual trajectory, moving too fast to be bound by the sun's gravity, confirmed that it had come from outside our solar system. From the moment of its discovery, Oumuamua sparked intense debate among scientists due to its highly unusual characteristics. Unlike typical asteroids or comets, Oumuamua did not display the typical coma or tail associated with comets, despite passing relatively close to the sun. Its shape was also unlike anything previously observed. Instead of being spherical or irregular like most asteroids, Oumuamua appeared to be extremely elongated, with some estimates suggesting it was up to 10 times longer than it was wide. This cigar-like or pancake-shaped object defied easy categorization, and its exact nature remains a subject of ongoing debate. One of the most puzzling aspects of Oumuamua was its unexpected acceleration as it moved away from the sun normally. Objects that approach the sun experience a gravitational pull that gradually slows them down as they move away. However, Oumuamua appeared to speed up slightly as it departed, a behavior typically associated with comets when the outgassing of vapor from their surfaces provides a small rocket boost. But Oumuamua's lack of a visible coma or tail made this explanation uncertain, leaving scientists with no definitive answer as to why it accelerated. Several hypotheses have been proposed to explain Oumuamua's strange behavior. One possibility is that it could be a fragment of a larger body that was torn apart by gravitational forces during a close encounter with a star or another massive object. In this scenario, the object's elongated shape might be the result of tidal stretching during such an event. Another theory suggests that Oumuamua could be a fragment of frozen nitrogen or hydrogen, which would sublimate, turn from a solid to a gas, without producing the typical dust and gas cloud seen in comets. This could account for the observed acceleration, though such objects are thought to be rare. Perhaps the most controversial idea is that Oumuamua could be artificial in origin, possibly a fragment of alien technology or a probe sent by an advanced civilization. While this idea remains speculative and has not gained widespread acceptance among scientists, it highlights how little we truly know about interstellar objects and the range of possibilities they present. While Oumuamua has long since departed the solar system and will never return, its brief visit was followed in 2019 by the discovery of a second interstellar object, 2I/Borisov. Unlike Oumuamua, Borisov was much more easily identifiable as a comet, complete with a visible coma and tail. Borisov's arrival was another historic event, as it gave astronomers their first chance to study a bona fide interstellar comet in detail. Observations of Borisov revealed that it contained material similar to comets from our own solar system, such as water vapor and carbon monoxide, suggesting that the basic ingredients for planetary formation are common across the galaxy. However, Borisov also had some unique properties that set it apart from solar system comets. For instance, its composition was found to be unusually rich in carbon monoxide, far more than is typically seen in local comets. This may indicate that Borisov originated in a colder region of its home star system, where carbon monoxide ice could form and persist. The differences and similarities between Borisov and solar system comets are providing valuable clues about the diversity of conditions in other star systems and the processes that shape them. The study of interstellar objects like Oumuamua and Borisov is still in its infancy, but their discoveries have opened up an entirely new field of research. These objects offer a unique opportunity to study material that formed around other stars and has traveled across the vast distances of interstellar space. By analyzing their compositions, trajectories, and behaviors, scientists can gain insights into the conditions in distant star systems and the processes that govern the formation of planets, moons, and other celestial bodies. One of the most exciting prospects in this field is the potential for future missions to intercept or study interstellar objects in more detail. While Oumuamua and Borisov were both detected after they had already entered and were moving through the solar system, leaving only a brief window for observations, there are proposals for dedicated missions that could be ready to launch the next time an interstellar object is detected. One such proposal is the Project Lyra concept, which aims to design a spacecraft capable of intercepting a future interstellar visitor. Such a mission would be a monumental technical challenge, requiring extremely fast launch speeds and advanced propulsion techniques, but the potential scientific payoff could be enormous. In addition to studying the objects themselves, researchers are also investigating how often interstellar objects pass through the solar system. Some estimates suggest that small interstellar objects could be passing through the solar system all the time, but their small size and faintness make them difficult to detect with current technology. As telescopes become more powerful and sensitive, it's likely that we will discover many more of these travelers in the coming years, giving scientists a larger sample to study. The study of interstellar objects also has profound implications for astrobiology and the search for life beyond Earth. If objects like Oumuamua and Borisov can travel between star systems, it raises the possibility that the ingredients for life, or even life itself, could be transported across interstellar distances. This idea, known as interstellar panspermia, suggests that life could spread from one star system to another, carried by interstellar comets, asteroids, or other objects that move between the stars. While there is no direct evidence for interstellar panspermia, the discovery of interstellar objects makes the idea more plausible and worth further investigation. Interstellar objects also challenge us to think about the broader context of planetary formation and the dynamics of star systems. While we have learned a great deal about the formation of planets, moons, and other bodies in our own solar system, the discovery of interstellar visitors allows us to extend those models to other parts of the galaxy. How do planetary systems form and evolve in environments vastly different from our own? What role do interstellar objects play in the exchange of material between star systems? These are just a few of the questions that interstellar objects can help answer. As we continue to explore the solar system and the wider galaxy, the study of interstellar objects is likely to become an increasingly important part of our efforts to understand the universe. Each new discovery provides a window into the processes that shape the cosmos on the grandest scales, from the birth of stars and planets to the exchange of material between distant star systems. Whether we eventually intercept one of these visitors with a spacecraft, uncover new evidence of their origins, or even find hints of life within their icy or rocky exteriors, interstellar objects represent an exciting new frontier in our quest to understand the cosmos. In the coming decades, as our telescopes and technologies improve, we can expect more interstellar objects to be discovered, each offering new surprises and insights into the vast and varied nature of the universe. These mysterious travelers from other star systems may carry with them the answers to some of the most fundamental questions about the origins of planets, life, and even the processes that govern the evolution of galaxies. Interstellar objects are the ultimate cosmic messengers, and their study promises to unlock new secrets about the distant reaches of space and the incredible diversity of planetary systems throughout the galaxy. As we continue our exploration of the universe, another field that holds tremendous potential is the study of exoplanets, planets that orbit stars outside our solar system. Since the first discovery of an exoplanet in 1992, the search for these distant worlds has exploded into one of the most dynamic areas of modern astronomy. Today, we know of thousands of exoplanets, and the pace of discovery is accelerating thanks to advanced telescopes and innovative detection methods. This ever-growing catalog of exoplanets is helping us not only understand the diversity of planetary systems, but also edge closer to answering one of humanity's most profound questions. Are we alone in the universe? The discovery of exoplanets revolutionized our understanding of planetary formation and expanded our view of the cosmos. Before the detection of these distant worlds, scientists relied on the planets of our own solar system to model how planetary systems might form. The prevailing theory, based largely on the structure of our solar system, suggested that gas giants like Jupiter and Saturn would form far from their host stars, while smaller, rocky planets like Earth would form closer to their stars, within a region where water could exist in liquid form. This simple model was quickly upended with the discovery of hot Jupiters, massive gas giants orbiting extremely close to their stars, in some cases completing an orbit in just a few days. These findings showed that planetary systems could be far more diverse and dynamic than we had ever imagined. One of the major challenges in discovering exoplanets is that they are difficult to observe directly. Most exoplanets are too small and too faint to be seen through traditional telescopes because their host stars outshine them by a wide margin. Instead, astronomers rely on indirect methods to detect these worlds. One of the most successful methods is the transit method, which involves observing the slight dimming of a star's light as a planet passes in front of it. This periodic dimming, known as a transit, can reveal not only the presence of a planet, but also its size and orbit. NASA's Kepler Space Telescope, launched in 2009, was instrumental in using the transit method to detect thousands of exoplanets, many of them in systems very different from our own. Another widely used technique is the radial velocity method, which detects the gravitational wobble of a star caused by the orbit of an unseen planet. As a planet orbits its star, the star moves slightly in response to the planet's gravity, causing a periodic shift in the star's light. By measuring this wobble, astronomers can infer the mass of the planet and its distance from the star. Together, these methods have provided astronomers with a detailed picture of the planets orbiting other stars and have helped to identify several key types of exoplanets, including super-Earths, mini-Neptunes, and gas giants. One of the most exciting aspects of exoplanet research is the discovery of planets in the habitable zone of their stars, the region where conditions might be just right for liquid water to exist on the planet's surface. Liquid water is considered essential for life as we know it, making planets in the habitable zone prime candidates in the search for extraterrestrial life. Among the most notable of these discoveries is the TRAPPIST-1 system, a nearby star system with 7 Earth-sized planets, 3 of which are located in the star's habitable zone. The TRAPPIST-1 system has become a focal point for astrobiologists, who are eager to determine whether any of these planets could support life. As the study of exoplanets has progressed, astronomers have developed more sophisticated models of planetary atmospheres, allowing them to search for signs of life, or biosignatures, in the atmospheres of distant worlds. By analyzing the light that passes through a planet's atmosphere during a transit, scientists can identify specific molecules, such as water vapor, methane, carbon dioxide, and oxygen, that could indicate the presence of biological processes. The James Webb Space Telescope, JWST, which launched in 2021, is expected to play a key role in this effort, with its advanced instruments capable of detecting the faintest signals from exoplanetary atmospheres. The search for biosignatures has already yielded tantalizing results. In 2020, astronomers announced the detection of phosphine in the atmosphere of Venus, a discovery that sparked a wave of excitement and debate. On Earth, phosphine is produced by biological processes in anaerobic environments, leading some researchers to speculate that it could be a sign of life on Venus. However, Venus's extreme surface conditions, temperatures hot enough to melt lead and clouds of sulfuric acid, make it an unlikely candidate for life as we know it. Nevertheless, the detection of phosphine reignited interest in the search for life in unexpected places and underscored the importance of studying planetary atmospheres in detail. One of the key questions driving exoplanet research is how common Earth-like planets are in the galaxy. The discovery of super-Earths, rocky planets larger than Earth but smaller than Neptune, suggests that planets similar in size and composition to Earth may be relatively common. However, determining whether these planets could support life depends on a host of factors, including the planet's atmosphere, temperature, and the presence of water. As astronomers gather more data on these planets, they are developing new ways to assess their habitability and identify the most promising candidates for further study. The growing catalog of exoplanets has also revealed the incredible diversity of planetary systems across the galaxy. While our solar system contains 8 planets in relatively stable orbits, many exoplanetary systems are far more chaotic, with planets in highly eccentric orbits, multiple planets packed into tight configurations, or even planets orbiting binary star systems. These discoveries have challenged long-held assumptions about how planetary systems form and evolve, leading to new models that account for the role of planetary migration, gravitational interactions, and other complex processes. One particularly intriguing class of exoplanets is the superpuff planets. Planets with extremely low densities that are much larger than they should be given their mass. These planets, which have been compared to cotton candy due to their low density, challenge our understanding of planetary formation. Some superpuff planets are thought to have thick hydrogen-helium atmospheres that account for their large sizes, but how such planets form and maintain such atmospheres remains a mystery. Studying these unusual worlds could provide new insights into the range of planetary types that exist and the processes that shape their evolution. The search for exoplanets has also expanded to include not just planets, but also moons around those planets, so-called exomoons. Although no exomoons have been definitively detected yet, they are expected to be common, just as moons are in our own solar system. Detecting exomoons is extremely challenging because they are smaller and dimmer than their host planets. But new techniques and telescopes are making progress toward identifying these elusive objects. Exomoons could have profound implications for the search for life, as they might provide additional habitats in planetary systems, especially if they orbit gas giants in the habitable zone. The study of exoplanets has also raised philosophical questions about the uniqueness of Earth and our place in the cosmos. For centuries, Earth was thought to be the only world capable of supporting life, but the discovery of potentially habitable planets around other stars has challenged this view. As we find more and more planets that might harbor life, we are forced to reconsider whether life on Earth is a rare phenomenon or if the universe is teeming with life, waiting to be discovered. In the coming decades, the search for exoplanets and extraterrestrial life will be further advanced by next-generation telescopes and missions. The European Space Agency's Plato mission, set to launch in the mid-2020s, will focus on detecting Earth-sized planets in the habitable zones of Sun-like stars. Meanwhile, NASA's Habitable Exoplanet Observatory, HabEx, and the Large UV/Optical Infrared Surveyor, LUVOIR, are proposed future missions that aim to directly image Earth-like exoplanets and study their atmospheres for signs of habitability and life. These missions will not only help us find more exoplanets, but also provide the detailed data needed to assess their potential for supporting life. By directly imaging these distant worlds, we will be able to see what they look like, study their climates, and search for the faint signatures of life. Such discoveries could revolutionize our understanding of biology, planetary science, and the nature of life itself. The study of exoplanets has already transformed our view of the universe, revealing that planets are far more common and diverse than we ever imagined. As we continue to explore these distant worlds, we are on the verge of answering some of the most profound questions about the origins of life, the nature of planetary systems, and the possibility that we are not alone in the universe. With each new discovery, the exoplanet revolution brings us closer to understanding the place of Earth and humanity within the vast cosmic landscape. As we continue to unravel the mysteries of the cosmos, the next frontier in space exploration and scientific inquiry will likely be the study of the outer solar system, particularly the distant and enigmatic Kuiper Belt and Oort cloud. These regions, far beyond the orbit of Neptune, contain some of the most primitive and least understood objects in the solar system. Exploring these icy worlds and the vast stretches of space they occupy could offer critical insights into the early formation of the solar system, the behavior of distant planetary systems, and the boundary between our solar system and interstellar space. The Kuiper Belt is a vast, disc-shaped region of space that extends from the orbit of Neptune at about 30 astronomical units, AU, from the Sun, to around 50 Australian dollars. It is home to a multitude of small, icy bodies, often referred to as Kuiper Belt objects, KBOs. These objects are remnants from the early solar system, composed of frozen gases, water ice, and rock. The most famous KBO is Pluto, which was reclassified as a dwarf planet in 2006. Pluto, along with other large KBOs like Eris, Haumea, and Make, has become a focus of study for understanding the outer regions of the solar system. The Kuiper Belt's importance lies in its role as a relic of the early solar system. When the solar system was forming, much of the material that didn't coalesce into planets was left behind in regions like the Kuiper Belt. This makes the belt a sort of cosmic time capsule that preserves the conditions and materials from billions of years ago. By studying KBOs, astronomers can gain insight into the processes that shape the solar system and influence the formation of planets. One of the most significant missions to explore the Kuiper Belt is NASA's New Horizons, which made its historic flyby of Pluto in 2015. This mission transformed our understanding of Pluto, revealing a world far more dynamic and complex than previously thought. New Horizons captured detailed images of Pluto's surface, showing vast nitrogen ice plains, towering mountains made of water ice, and evidence of glaciers and possible cryovolcanism. The spacecraft also discovered that Pluto has a thin atmosphere and a complex interaction with the solar wind. Following its successful Pluto flyby, New Horizons continued its journey deeper into the Kuiper Belt and in 2019 conducted a flyby of the KBO Arrokoth, formerly known as 2014 MU69. Arrokoth, a small, contact binary object, provided scientists with a glimpse into the primordial building blocks of the solar system. Its relatively undisturbed surface and composition suggest that it has remained largely unchanged since its formation, offering a window into the conditions that existed when the solar system was still in its infancy. The discoveries made by New Horizons have paved the way for future missions to explore the Kuiper Belt in more detail. While flybys provide valuable data, they offer only brief snapshots of these distant worlds. Future missions may focus on long-term exploration of KBOs, potentially deploying orbiters or landers to study their surfaces, atmospheres, and compositions more thoroughly. These missions would not only enhance our understanding of KBOs themselves, but also provide clues about how planetary systems beyond our own might evolve, especially those that contain distant, icy worlds similar to those in the Kuiper Belt. Beyond the Kuiper Belt lies the mysterious and even more distant Oort cloud, a spherical shell of icy bodies that surrounds the solar system at distances ranging from 2,000 to 100,000 Australian dollars. The Oort cloud is thought to be the source of long-period comets, those that take thousands or even millions of years to complete an orbit around the Sun. Unlike the Kuiper Belt, the Oort cloud has not yet been directly observed, as its objects are too far away and too small to be detected with current technology. However, its existence is inferred from the behavior of comets and the dynamics of the solar system. The Oort cloud is believed to contain trillions of icy objects, many of which were likely ejected from the inner regions of the solar system during its early formation. These objects may hold clues about the distribution of material in the early solar system and the processes that shape the outer regions of planetary systems. Studying the Oort cloud could also help scientists understand the role that comets play in delivering water and organic materials to planets, a process that may have been critical in the development of life on Earth. Exploring the Oort cloud presents significant challenges due to its extreme distance from the Sun. Reaching the inner edge of the Oort cloud would take decades, even with the fastest spacecraft we currently have. However, there are proposals for missions that could begin to study the region more closely. One such concept is the interstellar probe, which would be designed to travel beyond the Kuiper belt and into the interstellar medium, passing through the outer reaches of the solar system and potentially observing Oort cloud objects along the way. In addition to studying the solar system's boundary regions, the interstellar probe would also aim to explore the heliosphere, the bubble of space dominated by the Sun's influence. The heliosphere is created by the solar wind, a stream of charged particles emitted by the Sun, which interacts with the interstellar medium. The edges of the heliosphere, known as the heliopause, mark the transition between the space dominated by the Sun and true interstellar space. Studying this boundary is important for understanding how the solar wind interacts with the interstellar medium and how other star systems might behave. The Voyager 1 and 2 spacecraft, launched in 1977, have already crossed the heliopause and entered interstellar space, making them the first human-made objects to leave the solar system. However, they were not designed to study the Kuiper belt or Oort cloud in detail, and their instruments are now limited by their age and distance from Earth. A dedicated mission like the interstellar probe could provide much more detailed data about these regions, as well as help answer fundamental questions about the structure of the solar system's outermost boundaries. The study of the Kuiper belt, the Oort cloud, and the outer regions of the solar system also has implications for understanding exoplanetary systems. Many of the exoplanets discovered to date orbit far from their parent stars, and some are surrounded by disks of debris similar to the Kuiper belt. By studying how our own solar system's outer regions formed and evolved, we can develop better models for how other planetary systems might be structured. These comparisons can help us identify patterns and processes that are universal to planetary formation or unique to certain types of systems. One of the most intriguing prospects in the exploration of the outer solar system is the potential for discovering new, distant planets. In recent years, there has been growing evidence for the existence of a ninth planet, often referred to as Planet 9 or Planet X, located far beyond the orbit of Neptune. The orbits of certain distant objects in the Kuiper belt appear to be influenced by the gravity of an unseen massive object, leading some scientists to hypothesize that a large, undiscovered planet may be lurking in the far reaches of the solar system. Planet 9, if it exists, would likely be a gas giant similar in size to Neptune or Uranus, and it could be orbiting the Sun at a distance of several hundred AU. Detecting such a planet is extremely challenging due to its distance and faintness, but astronomers are actively searching for it using powerful telescopes and new data analysis techniques. If Planet 9 is discovered, it would not only be a major scientific breakthrough, but also reshape our understanding of the solar system's structure and dynamics. The outer solar system is a frontier that holds countless mysteries. Whether it's the discovery of new planets, the study of primordial objects in the Kuiper belt, or the investigation of the distant Oort cloud, the exploration of these regions promises to deepen our understanding of the solar system's origins and evolution. As new missions are developed and launched, we stand on the brink of a new era of discovery, where the outermost reaches of our cosmic neighborhood may finally reveal their secrets. In the next few decades, with the advancement of space exploration technologies and the increasing power of telescopes, we may uncover answers to some of the most fundamental questions about our solar system. How did it form? How did it evolve? And what lies beyond its outermost boundaries? These icy worlds, hidden in the farthest corners of the solar system, may hold the keys to understanding not only our own place in the cosmos, but also the nature of planetary systems throughout the galaxy. As we continue our exploration of the outer reaches of the solar system, the next grand chapter in space exploration focuses on the possibility of human missions to Mars, a long-anticipated and monumental goal that could change the trajectory of human history. Mars, often referred to as the Red Planet, has captivated the imagination of scientists, engineers, and space enthusiasts for decades. Now, with major advancements in technology, the efforts of space agencies like NASA, private companies such as SpaceX, and international collaborations, the dream of landing humans on Mars is closer than ever before. A human mission to Mars represents not only a significant leap in space exploration, but also a profound step toward humanity becoming an interplanetary species. Mars, the fourth planet from the Sun, is the most Earth-like of all the planets in the solar system. With a day length nearly identical to Earth's and polar ice caps made of water and carbon dioxide, it offers an environment that, while harsh, is theoretically within the realm of human habitation. The planet has been a key target for astrobiology because of evidence suggesting that it once had liquid water on its surface, raising the possibility that microbial life could have existed there in the distant past, or might still exist beneath the surface. The path to Mars has been paved by a series of robotic missions that have vastly expanded our understanding of the planet. Over the last few decades, NASA's Mars rovers, starting with Sojourner in 1997 and followed by Spirit, Opportunity, Curiosity, and Perseverance, have explored the planet's surface, gathering invaluable data about its geology, climate, and the potential for life. The Perseverance rover, which landed on Mars in 2021, is currently conducting some of the most advanced scientific experiments ever performed on the planet. It is also preparing for a future sample return mission that will bring Martian rocks and soil back to Earth for the first time. But while robotic exploration has been essential in preparing for a human mission, sending humans to Mars presents a host of challenges that go far beyond what robotic missions have faced. A human mission to Mars involves overcoming a wide range of obstacles, from the technical and logistical to the physiological and psychological. The distance to Mars is a key challenge. At its closest, Mars is still about 54.6 million kilometers, 33.9 million miles from Earth, and a round-trip mission could take up to 2 or 3 years. Unlike the Apollo missions to the Moon, which lasted just over a week, astronauts on a Mars mission would face long periods of isolation and exposure to the hazards of deep space. One of the primary concerns for a human mission to Mars is radiation exposure. Unlike Earth, Mars does not have a global magnetic field or a thick atmosphere to shield its surface from cosmic radiation and solar particles. Astronauts traveling to and living on Mars would be exposed to much higher levels of radiation than they are in low Earth orbit. Prolonged exposure to this radiation increases the risk of cancer and other health problems, so designing adequate protection, both for the journey to Mars and for a prolonged stay on the Martian surface, is one of the mission's most pressing challenges. Some solutions involve building habitats underground or using Martian regolith soil to create thick walls that can shield astronauts from radiation. Another significant challenge is life support and sustainability. On Mars, there is no breathable air, liquid water on the surface, or abundant food sources, meaning that all the resources necessary for human survival would have to be brought from Earth or generated in situ. This has led to the development of in-situ resource utilization, ISRU, technologies, which are designed to make use of local materials to produce essential resources. For example, Mars' atmosphere is composed mostly of carbon dioxide, and scientists have already demonstrated technology that can convert this CO2 into oxygen. The Perseverance rover is testing one such technology, known as MOXIE, Mars Oxygen In-Situ Resource Utilization Experiment, which is capable of generating oxygen from the Martian atmosphere, potentially paving the way for future missions to use this process to produce breathable air and even rocket fuel. Water is another critical resource. While liquid water does not exist on Mars' surface today, there is evidence of frozen water at the polar ice caps and possibly underground. If future missions can locate and extract this water, it could be used not only for drinking and growing food, but also for producing oxygen and hydrogen through electrolysis, providing both air and fuel for astronauts. Successfully developing these resource generation systems would make Mars missions far more sustainable and reduce the need to launch vast quantities of supplies from Earth. In terms of food, long-duration missions to Mars will require new approaches to growing food in space. NASA and other space agencies have been experimenting with space agriculture, testing different methods of growing crops in controlled environments on the International Space Station, ISS. On Mars, astronauts would need to grow their own food in greenhouses, using artificial lighting or the limited sunlight that reaches the planet's surface. Mars soil is not suitable for farming without treatment. So future missions may also experiment with creating nutrient-rich soil using composting or hydroponic systems, which can grow plants without soil by providing nutrient-enriched water directly to their roots. The psychological and social challenges of a human mission to Mars are also substantial. Astronauts will need to endure long periods of isolation, confinement, and distance from Earth, with communication delays of up to 20 minutes each way due to the vast distance between the planets. This isolation could lead to significant psychological stress, and space agencies are developing support systems to help astronauts cope with the mental health challenges of such a mission. The close quarters, limited social interaction, and high-stakes nature of the mission will require astronauts to be resilient, adaptable, and capable of working well in a team under extreme pressure. Despite these challenges, plans for human missions to Mars are progressing rapidly. NASA has set a target date of the 2030s for its first crewed mission to Mars as part of its Artemis program, which aims to return humans to the Moon by 2024 and use the Moon as a stepping stone for deep space exploration. The Artemis program is critical to the Mars effort, as it will help develop the technologies, systems, and experience needed for a longer, more complex mission to the Red Planet. At the same time, private companies like SpaceX are aggressively pursuing their own plans for Mars exploration. SpaceX, led by Elon Musk, has outlined an ambitious vision of establishing a permanent, self-sustaining human colony on Mars within the next few decades. The company's Starship spacecraft, currently under development, is designed to be fully reusable and capable of carrying large crews and significant cargo to Mars. SpaceX has already conducted early test flights of Starship and aims to use it not only for Mars missions, but also for lunar landings and other deep space missions. One of the central motivations for human exploration of Mars is the idea of ensuring the survival of humanity by becoming a multiplanetary species. Mars represents the most viable option for human colonization within the solar system. While it is a harsh and unforgiving environment, it offers the potential for terraforming or altering its environment to make it more Earth-like. Some scientists believe that, over centuries or millennia, it might be possible to warm Mars' atmosphere and create conditions that could support liquid water and more sustainable human settlements. This vision, though far in the future, is driving many of the efforts to study Mars today. The scientific benefits of sending humans to Mars are also immense. Astronauts on the Martian surface could conduct detailed geological studies, search for signs of past or present life, and help unlock the mysteries of the planet's climate and atmosphere. While robotic rovers have made incredible discoveries, humans on Mars would bring unparalleled capabilities for exploration and scientific inquiry. They could operate more complex instruments, make real-time decisions, and conduct hands-on experiments that are impossible with current technology. Human presence on Mars would also inspire a new generation of scientists, engineers, and explorers, pushing the boundaries of what is possible and driving innovation in a wide range of fields. Ultimately, a human mission to Mars is not just about exploration for exploration's sake. It is about pushing the limits of human potential, expanding our knowledge of the universe, and laying the groundwork for humanity's long-term survival and growth beyond Earth. The journey to Mars will be one of the most challenging and ambitious endeavors ever undertaken, but it will also be one of the most rewarding, opening new frontiers for science, discovery, and the future of life in the cosmos. As we stand on the cusp of this new era, Mars beckons as both a destination and a symbol of our relentless pursuit of knowledge. Whether through the efforts of government space agencies, private industry, or international collaboration, the human journey to Mars will redefine what it means to explore and inhabit space. In the coming decades, as the first footprints are left on the surface of the Red Planet, we will be writing the next great chapter in the story of humanity's place in the universe. A story that began with our ancestors gazing up at the stars and continues now with our first steps toward becoming a true spacefaring civilization. As we look beyond Mars and deeper into the future of space exploration, one of the most exciting prospects is the potential for human and robotic missions to the outer planets and their moons. These distant worlds, Jupiter, Saturn, Uranus, and Neptune, hold many secrets about the formation of our solar system, and their moons, in particular, are some of the most intriguing targets in the search for extraterrestrial life. While the journey to these far-flung planets poses immense technical and logistical challenges, the scientific rewards could be extraordinary, revealing entirely new environments and answering profound questions about the potential for life in the universe. Among the outer planets, Jupiter and Saturn have received the most attention due to their complex systems of moons, rings, and magnetic fields. Jupiter's moons, especially Europa, Ganymede, and Callisto, along with Saturn's moon Enceladus, are some of the top candidates for hosting life within the solar system. These moons are thought to harbor subsurface oceans beneath their icy crusts, where liquid water could provide the conditions necessary for life to exist. If life does exist in these hidden oceans, it would revolutionize our understanding of biology and the conditions under which life can thrive. Europa, one of the largest moons of Jupiter, has long been considered a prime candidate in the search for life. With a smooth, icy surface crisscrossed by ridges and cracks, Europa is believed to have a vast ocean of liquid water beneath its ice shell, kept warm by tidal forces generated by Jupiter's gravity. These tidal forces create friction in Europa's interior, producing heat that prevents the water from freezing solid. Similar processes occur on Earth's icy moons like Enceladus, suggesting that oceans beneath ice shells could be common in the solar system. What makes Europa so compelling is the possibility that hydrothermal vents may exist on its ocean floor, much like those found on Earth's seafloors. On Earth, these vents are home to thriving ecosystems, where life derives energy from chemicals in the water rather than sunlight, a process known as chemosynthesis. If similar conditions exist on Europa, it could mean that life could have evolved in its deep ocean, making it one of the most exciting targets for future missions. NASA's upcoming Europa Clipper mission, set to launch in the mid-2020s, will investigate Europa's potential habitability by conducting detailed flybys of the moon. Europa Clipper will be equipped with instruments designed to study the thickness of Europa's ice shell, the depth and composition of its ocean, and the potential for hydrothermal activity on the seafloor. While Europa Clipper will not land on the surface, it will provide crucial data that could inform future lander missions, which could directly sample Europa's ice or search for signs of life in plumes of water vapor that may be erupting from cracks in the ice. In addition to Europa, Saturn's moon Enceladus has emerged as one of the most promising places to search for extraterrestrial life. Like Europa, Enceladus has a subsurface ocean beneath its icy crust, and it has been observed spewing plumes of water vapor and ice particles from its south pole. These plumes were discovered by NASA's Cassini spacecraft, which flew through them and detected organic molecules, salts, and evidence of hydrothermal activity on the ocean floor. The presence of these ingredients for life has led many scientists to believe that Enceladus is one of the best places to search for life beyond Earth. Future missions to Enceladus could include orbiters, landers, or even probes designed to dive through the plumes and directly sample the material ejected from the moon's ocean. These missions could search for microbial life or chemical signatures that indicate biological processes, providing a direct test of whether life exists beyond Earth. One proposed mission, the Enceladus Life Finder, aims to send a spacecraft equipped with instruments capable of analyzing the organic molecules in the plumes to determine if they are produced by biological or non-biological processes. While Europa and Enceladus have captured much of the attention in the search for life, other moons in the outer solar system are also compelling targets. Ganymede, the largest moon of Jupiter, is believed to have a layered structure with multiple oceans of liquid water beneath its surface, making it another candidate for future exploration. Ganymede is unique in that it is the only moon known to have its own magnetic field, which could help protect its subsurface ocean from harmful cosmic radiation, potentially providing a more stable environment for life. The European Space Agency's JUICE, Jupiter Icy Moons Explorer, mission, set to launch in 2022, will focus on Ganymede, Europa, and Callisto, another large moon of Jupiter. JUICE will conduct detailed studies of these moons, investigating their potential for habitability and providing important data on the characteristics of their ice shells and subsurface oceans. The mission is expected to arrive at Jupiter in 2029 and spend several years orbiting the giant planet, conducting multiple flybys of its moons and eventually entering orbit around Ganymede itself. While Jupiter's moons offer tantalizing prospects for exploration, Saturn's system also holds numerous scientific opportunities. In addition to Enceladus, Saturn's largest moon, Titan, presents a wholly different kind of environment that may support life, albeit one very different from life as we know it. Titan has a thick atmosphere, rich in nitrogen and hydrocarbons, and its surface is covered in lakes and seas of liquid methane and ethane. Despite its frigid temperatures, Titan's unique chemistry and surface conditions make it an exciting target for studying prebiotic chemistry, the chemical processes that could give rise to life. NASA's Dragonfly mission, scheduled to launch in 2027, will send a rotorcraft to Titan's surface to explore its diverse landscapes, including dunes, lakes, and potential cryovolcanoes. Dragonfly will be capable of flying across Titan's surface, taking samples of its atmosphere and surface materials to search for complex organic molecules and chemical processes that could lead to life. Titan's methane seas and organic-rich environment offer a natural laboratory for studying how life might arise in environments vastly different from Earth. While the moons of Jupiter and Saturn have received the most attention in the search for life, the ice giants Uranus and Neptune, along with their moons, represent largely unexplored frontiers. These distant planets have been visited only once during the Voyager 2 flybys in the 1980s, and much of what we know about them remains speculative. Both Uranus and Neptune are surrounded by systems of moons and rings, and their interiors may hold clues about planetary formation, the dynamics of gas giants, and even the potential for hidden oceans beneath the surfaces of some of their moons. Miranda, a moon of Uranus, has one of the most bizarre and varied surfaces in the solar system, with towering cliffs, ridges, and regions that appear to have been reshaped by internal geological processes. Triton, Neptune's largest moon, is equally fascinating. Triton orbits Neptune in a retrograde direction, meaning it moves in the opposite direction to Neptune's rotation. This suggests that Triton may have been captured from the Kuiper Belt and was once a dwarf planet. Triton has geysers that spew nitrogen gas, and its surface shows evidence of cryovolcanism, indicating that it may have a subsurface ocean as well. Proposed missions to the ice giants include orbiters that would study the atmospheres, rings, and magnetospheres of Uranus and Neptune, as well as probes that could investigate their moons in detail. These missions would provide valuable data about the outer regions of the solar system and offer comparisons with the more well-studied gas giants Jupiter and Saturn. Understanding the ice giants is also critical for studying exoplanetary systems, as many of the exoplanets discovered so far are ice giants or gas giants similar to Uranus and Neptune. Exploring the outer planets and their moons requires overcoming significant technical challenges. The vast distances involved mean that missions to these distant worlds take many years to reach their destinations. Communication delays and the harsh environments of the outer solar system add to the complexity, requiring spacecraft to be highly autonomous and capable of operating in extreme cold, with little sunlight to power their systems. Nonetheless, the scientific rewards of exploring these distant worlds are enormous, offering the potential to uncover entirely new ecosystems, geological processes, and environments that could harbor life. As we push farther into the outer solar system, these missions will deepen our understanding of planetary formation, the conditions for life, and the broader dynamics of the solar system. The exploration of Jupiter, Saturn, Uranus, and Neptune, and their moons, represents the next great leap in humanity's quest to explore the cosmos. These icy moons and distant planets hold the promise of discoveries that could reshape our understanding of the universe, and perhaps even reveal that life exists beyond Earth, hidden beneath the ice of distant worlds. The pursuit of knowledge and the drive to explore are inherent to humanity, and as we reach farther into the depths of space, we continue to push the boundaries of what we know and what we can achieve. The outer planets are waiting for us, and as our technology and ambition grow, we will unlock their mysteries, continuing the journey that began with our first steps beyond Earth and leading us ever deeper into the wonders of the cosmos. As humanity ventures even further into the outer reaches of space, the next truly monumental step in our exploration will be the journey beyond our own solar system, toward the stars. This ultimate goal, interstellar exploration, remains one of the most ambitious challenges in science and engineering. The sheer distances involved are mind-boggling. The closest star to our Sun, Proxima Centauri, is over 4.24 light-years away, or about 40 trillion kilometers. Even with the fastest spacecraft we've ever built, it would take tens of thousands of years to reach another star. However, recent technological advancements, combined with a growing sense of possibility, are pushing the boundaries of what we once thought was impossible. With new concepts in propulsion, miniaturized technology, and visionary projects like Breakthrough Starshot, the dream of sending a probe to another star system may soon become a reality. The most immediate target for interstellar exploration is the Alpha Centauri system, the closest stellar neighbor to our solar system. Alpha Centauri is a triple star system, consisting of two sun-like stars, Alpha Centauri A and B, and a smaller red dwarf, Proxima Centauri. Proxima Centauri is of particular interest because in 2016, astronomers discovered an Earth-sized exoplanet orbiting within its habitable zone, where conditions could allow liquid water to exist. This planet, known as Proxima b, is one of the most promising candidates for the search for life beyond our solar system. A mission to Proxima b could revolutionize our understanding of planets around other stars, their potential habitability, and whether life might exist elsewhere in the universe. One of the most exciting proposals for interstellar exploration is the Breakthrough Starshot Initiative, a project launched in 2016 by the Breakthrough Initiatives, a scientific program backed by prominent figures like physicist Stephen Hawking, entrepreneur Yuri Milner, and Facebook founder Mark Zuckerberg. The goal of Breakthrough Starshot is to send tiny, lightweight spacecraft, about the size of a postage stamp, toward the Alpha Centauri system using groundbreaking new propulsion technology. Instead of using conventional rockets, the project proposes using a powerful laser array on Earth to propel a fleet of small star chips attached to light sails. These light sails, which would be just a few meters wide but incredibly thin, would catch the energy from the laser beams and accelerate the star chips to an astonishing 20% of the speed of light. At this speed, approximately 60,000 kilometers per second, these tiny spacecraft could reach the Alpha Centauri system in just over 20 years, a time frame that makes the concept of interstellar exploration within our lifetimes suddenly seem possible. Once they arrived, the star chips would fly past Proxima b and its host stars, capturing data and sending it back to Earth. Though the data transmission would take just over 4 years to reach us, the information gained could be invaluable, providing the first detailed look at a planet orbiting another star. The engineering challenges of Breakthrough Starshot are immense, but the project has generated enormous excitement and spurred innovation in fields like miniaturization, materials science, and laser propulsion. One of the key advantages of using tiny spacecraft is that they are much easier to accelerate to high speeds than larger, heavier vehicles. However, ensuring that these small star chips can survive the journey, navigate the vast distances of interstellar space, and send useful data back to Earth remains a significant hurdle. Moreover, building a laser array capable of delivering the necessary energy is a monumental engineering task, one that would require international collaboration and likely take years or even decades to complete. Nevertheless, Breakthrough Starshot represents a bold step toward interstellar exploration, and its technological advancements could have profound ripple effects for space exploration in general. If the project succeeds, it could pave the way for other missions to more distant star systems, potentially even enabling humanity to explore planets around stars that are tens or hundreds of light years away. The development of such advanced propulsion technologies could also lead to breakthroughs in space travel within our own solar system, making missions to the outer planets or even future human expeditions to Mars and beyond faster and more feasible. In addition to Breakthrough Starshot, other concepts for interstellar travel are being explored, including nuclear propulsion, antimatter engines, and even hypothetical concepts like warp drives. One of the more realistic near-term proposals is nuclear fusion propulsion, which could provide the energy necessary to power spacecraft on interstellar journeys. Fusion propulsion relies on the same process that powers the sun, fusing atomic nuclei together to release massive amounts of energy. While nuclear fusion has yet to be harnessed for terrestrial energy generation, researchers believe it could offer an incredibly efficient and powerful propulsion system for future deep space missions. Antimatter propulsion, another theoretical technology, would involve using matter and antimatter collisions to produce energy, as antimatter annihilates ordinary matter in a burst of pure energy. While producing and storing antimatter remains a major challenge, such a propulsion system could potentially accelerate spacecraft to a significant fraction of the speed of light, making interstellar journeys more achievable within human timescales. Both fusion and antimatter propulsion are in the early stages of research, but they represent exciting possibilities for the future of space travel. Even more speculative are concepts like the warp drive, which would allow faster-than-light travel by bending or warping space-time itself. This idea, rooted in Einstein's theory of general relativity, gained popular recognition thanks to science fiction, particularly Star Trek. While no evidence currently supports the feasibility of a warp drive, theoretical physicists have explored the concept in greater detail, with some suggesting that such a drive could be possible in the distant future, provided we could find a way to manipulate space-time and generate negative energy, a substance that has yet to be observed. Despite the challenges, interstellar exploration offers enormous scientific potential. The discovery of thousands of exoplanets in recent decades has fundamentally altered our understanding of the universe, revealing that planets are common around other stars. Many of these planets reside in the habitable zones of their stars, where conditions could allow for the presence of liquid water and, by extension, the possibility of life. Exploring these planets up close would allow us to directly test theories about planetary formation, atmospheres, climates, and the conditions necessary for life. One of the most profound scientific questions remains whether life exists beyond Earth. The discovery of microbial life on another planet, or the detection of complex biosignatures in the atmosphere of an exoplanet, would revolutionize biology and our understanding of life's origins. If life is found to be common in the universe, it would suggest that the conditions for life are not unique to Earth, and that the universe could be teeming with diverse forms of life. Conversely, if we find no evidence of life on other planets, it would raise deep questions about why Earth is so special and what factors might limit the emergence of life elsewhere. In addition to the search for life, interstellar exploration could help answer fundamental questions about the nature of the universe. For example, studying the environments around other stars could provide insights into the formation of planetary systems and the evolution of galaxies. By visiting distant star systems, we could learn more about stellar dynamics, the behavior of different types of stars, and the processes that shape planetary orbits and habitability. Such knowledge would not only expand our understanding of astrophysics, but also inform our search for habitable worlds and the conditions that support life. Interstellar exploration also forces us to think on the grandest of timescales, contemplating the future of humanity and the potential for life to spread beyond Earth. The idea of humanity becoming a multi-stellar species may seem like the stuff of science fiction today, but the seeds of that future are being planted now with projects like Breakthrough Starshot and research into advanced propulsion technologies. As we look ahead to the coming centuries, the idea that humans, or our robotic emissaries, might explore not just the solar system, but the entire galaxy becomes more than a distant dream. It becomes a plausible goal for the long-term future of our species. However, the challenges are not just technical. Interstellar exploration will also require international cooperation, long-term commitment, and ethical considerations. As we venture farther into the cosmos, we will need to develop new frameworks for governance, ensuring that space exploration benefits all of humanity and does not replicate the mistakes of past explorations on Earth. Questions about the environmental impact of space exploration, the preservation of extraterrestrial environments, and the potential for contact with other forms of life will need to be addressed as we embark on this new chapter of exploration. In the meantime, The path to the stars will be paved with incremental but important steps. Missions to the outer planets, the continued search for exoplanets, and the development of advanced space technologies will all contribute to our eventual ability to explore the universe beyond our solar system. Each new discovery brings us closer to understanding our place in the cosmos. And with each breakthrough, the dream of interstellar travel becomes a little more tangible. As we stand on the threshold of a new era in space exploration, the stars beckon to us as they always have, calling us to explore, discover, and push the boundaries of what is possible. Whether through the launch of tiny probes like those envisioned in Breakthrough Starshot, the development of revolutionary propulsion technologies, or the eventual journey of humans to distant worlds, the quest for the stars represents the next great adventure for humanity. It is a journey that will define the future of our species, reshape our understanding of the universe, and perhaps, one day, lead us to new homes among the stars. As we extend our gaze beyond the stars and into the farthest reaches of the cosmos, the next bold leap in our quest for understanding is the study and eventual exploration of black holes and other exotic cosmic phenomena. These enigmatic objects, where gravity is so intense that not even light can escape, represent some of the most profound mysteries in modern physics. Black holes, neutron stars, and the strange behavior of space-time at the edge of these celestial bodies challenge our understanding of the fundamental laws of the universe. Delving into their nature offers a glimpse into the extremes of reality itself, where the known rules of physics break down, and new, unexplored territories of science await discovery. Black holes, in particular, have captured the imagination of both scientists and the public alike. For decades, they were theoretical predictions of Einstein's general theory of relativity. But in recent years, we have moved from indirect evidence to direct observation. The 2019 image of the supermassive black hole at the center of the galaxy M87, captured by the Event Horizon Telescope, EHT, marked a milestone in astrophysics. This historic image provided the first visual confirmation of a black hole's event horizon, the boundary beyond which nothing can return. This achievement, however, is just the beginning of what promises to be a golden age of black hole research, as scientists prepare to probe deeper into these mysterious objects. One of the most pressing questions in black hole research is understanding what happens at the very core of a black hole: the singularity. According to general relativity, a singularity is a point of infinite density where the laws of physics, as we know them, cease to operate. Time, space, and matter collapse into a single point, and our current understanding of the universe breaks down. However, general relativity does not account for quantum mechanics, the branch of physics that governs the behavior of particles on the smallest scales. This gap in our knowledge, where the laws of general relativity and quantum mechanics must be reconciled, is known as the quantum gravity problem. To solve this problem, scientists are searching for a theory of quantum gravity, a unified theory that would bring together the large-scale mechanics of general relativity with the subatomic rules of quantum mechanics. Understanding black holes is central to this quest because they represent one of the few environments in the universe where both quantum effects and extreme gravitational forces play a significant role. The study of black holes could ultimately lead to the discovery of a theory of everything, a single framework that explains all the fundamental forces of nature. One of the most famous paradoxes in black hole physics is the black hole information paradox. According to classical theory, anything that crosses a black hole's event horizon is lost forever, including any information about its physical state. However, quantum mechanics dictates that information cannot be destroyed. This conflict between the two theories has led to intense debate among physicists. Some researchers propose that information may be stored at the event horizon itself, encoded in what is called black hole entropy, while others suggest that black holes might eventually evaporate over time due to a process known as Hawking radiation, named after physicist Stephen Hawking, who proposed that black holes emit faint radiation and slowly lose mass. The discovery of Hawking radiation was groundbreaking because it suggested that black holes are not completely black. They emit radiation due to quantum effects near the event horizon. Over eons, This process could cause black holes to shrink and eventually disappear. However, the fate of the information that falls into a black hole remains a mystery. Some physicists have suggested that the information may be preserved in a highly scrambled form in the radiation, but no definitive answer has been found yet. This paradox lies at the heart of efforts to reconcile general relativity and quantum mechanics. To explore these questions, new observational tools are being developed that will allow scientists to study black holes with greater precision than ever before. The Event Horizon Telescope, which produced the first image of a black hole, is being upgraded to capture more detailed images and study a wider range of black holes. By observing the event horizons of supermassive black holes at the centers of galaxies, researchers hope to test theories about how black holes spin, how they interact with their surroundings, and how matter behaves in the extreme conditions near the event horizon. In addition to direct observations of black holes, gravitational wave astronomy is opening up a new window into the universe. Gravitational waves, first predicted by Einstein and detected for the first time in 2015 by the LIGO and Virgo observatories, are ripples in space-time caused by the acceleration of massive objects, such as the collision and merger of black holes or neutron stars. These waves carry information about the most violent and energetic processes in the universe, allowing scientists to detect events that would otherwise be invisible. Each new detection of gravitational waves provides valuable data about the nature of black holes, their masses, their spins, and the environments in which they exist. The study of gravitational waves is not limited to black holes. Neutron stars, extremely dense remnants of supernova explosions, also generate gravitational waves when they merge or interact with each other. These objects are so dense that a sugar cube-sized portion of neutron star material would weigh as much as a mountain. Like black holes, neutron stars push the limits of our understanding of physics, particularly in the areas of nuclear physics and the behavior of matter under extreme conditions. The collision of two neutron stars, detected in 2017 and dubbed GW170817, was a landmark discovery. Not only did it generate gravitational waves, but it also produced a flash of light detected by telescopes across the electromagnetic spectrum. This event provided the first direct confirmation that neutron star mergers are responsible for the creation of heavy elements like gold and platinum. The study of neutron stars and gravitational waves is helping scientists understand the fundamental forces that govern matter and energy in the most extreme environments. Beyond black holes and neutron stars, other exotic cosmic phenomena are being studied with increasing interest. Fast radio bursts, FRBs, are one such mystery. These are incredibly brief, intense bursts of radio waves that originate from distant galaxies. First discovered in 2007, FRBs have become one of the most puzzling phenomena in astrophysics. Their origin and cause are still unknown, but some theories suggest they could be related to highly magnetized neutron stars, magnetars, black hole activity, or even entirely new astrophysical processes. As more FRBs are detected, patterns have begun to emerge. Some FRBs repeat at irregular intervals, while others appear to be one-off events. The discovery of repeating FRBs has allowed astronomers to pinpoint their locations within galaxies, offering clues about their origins. One of the most exciting possibilities is that FRBs could be linked to the activity of magnetars, which are neutron stars with incredibly powerful magnetic fields. These fields are so strong that they can distort atomic structures and produce intense bursts of radiation. Understanding the nature of FRBs could lead to the discovery of new physical processes and expand our understanding of the most extreme objects in the universe. Another tantalizing area of research involves the hypothetical existence of primordial black holes that may have formed in the very early universe, shortly after the Big Bang. Unlike the black holes we know, which form from the collapse of massive stars, primordial black holes would have formed directly from the high-density fluctuations in the early universe. These black holes could range in size from tiny, microscopic black holes to massive objects, and they could help explain the nature of dark matter, which makes up about 85% of the matter in the universe, but remains invisible and undetected by conventional means. Some theories suggest that primordial black holes could account for some or all of the dark matter in the universe. If so, detecting them would not only provide evidence for these elusive objects, but also solve one of the greatest mysteries in modern astrophysics: the true nature of dark matter. Upcoming missions, such as the European Space Agency's Euclid satellite, which is designed to map the distribution of dark matter and dark energy, may provide new clues about whether primordial black holes exist and how they might be detected. The exploration of black holes, neutron stars, and other cosmic phenomena is taking us to the very limits of our understanding of the universe. These objects challenge our current theories and offer tantalizing hints of new physics waiting to be discovered. As technology improves and our ability to observe these extreme environments grows, we are likely to make new breakthroughs that will reshape our understanding of space, time, and the fundamental nature of reality. The quest to understand these exotic objects is more than just a scientific endeavor. It is a journey that takes us to the edges of human knowledge, where the mysteries of the cosmos become intertwined with the deepest philosophical questions about the nature of existence. What happens inside a black hole? Can the universe be fully explained by our current theories? Or are we on the cusp of discovering new laws of physics that will revolutionize our understanding of reality? These questions drive the exploration of the cosmos and will continue to inspire future generations of scientists, engineers, and dreamers. As we push the boundaries of space exploration, black holes and other extreme objects will remain at the forefront of our quest for knowledge, challenging us to confront the unknown and expand the limits of what we believe to be possible. As we journey further into the depths of cosmic inquiry, one of the most intriguing and mysterious realms we are beginning to explore is the nature of dark matter and dark energy, two components that together make up about 95% of the universe, yet remain almost entirely unknown to us. While ordinary matter, the stuff of stars, planets, and galaxies, accounts for only about 5% of the universe's total energy and mass, dark matter and dark energy are believed to govern the large-scale structure and fate of the cosmos. Understanding these two forces could unlock answers to fundamental questions about the universe's origins, its structure, and its ultimate destiny. Dark matter was first hypothesized in the early 20th century when astronomers noticed that galaxies appeared to contain much more mass than what could be accounted for by the visible stars and gas. Galaxies spin too quickly for the amount of visible matter they contain. Their stars should be flung out into space by centrifugal forces if gravity alone, as we understand it, were the only factor. Yet, these galaxies remain intact, leading scientists to conclude that there must be some invisible, or dark, matter present that exerts gravitational influence on the visible matter, holding galaxies together. Since then, a wealth of evidence has confirmed the existence of dark matter, including observations of galaxy clusters, gravitational lensing, the bending of light by gravity, and the cosmic microwave background, the faint afterglow of the Big Bang. However, despite its abundance, we have yet to detect dark matter directly. It does not interact with light, making it invisible to telescopes, and it interacts only weakly, if at all, with ordinary matter, which makes it extremely difficult to study. The only force it seems to interact with is gravity. The leading candidates for dark matter are hypothetical particles called WIMPs, weakly interacting massive particles. WIMPs are thought to be very massive, but they interact only through the weak nuclear force and gravity, which makes them nearly impossible to detect in everyday life. Scientists have built extremely sensitive detectors deep underground, such as the Xenon 1T experiment in Italy and the LUX Zeppelin experiment in the United States, to search for rare interactions between dark matter particles and ordinary matter. These detectors are placed deep underground to shield them from cosmic rays and other sources of background radiation that could interfere with the detection of dark matter particles. Despite decades of effort, no conclusive detections have been made, though each new experiment pushes the limits of our ability to detect these elusive particles. Another promising candidate for dark matter is axions, another type of hypothetical particle that would be much lighter than WIMPs, but could explain the same gravitational effects. Axions are predicted to have a very low mass and could behave more like waves than particles, filling the universe in a way that explains the gravitational effects we observe. Scientists are currently building experiments to search for axions, including the Axion Dark Matter Experiment, ADMX, and other advanced technologies that aim to detect these incredibly faint signals. A more exotic possibility is that dark matter could be composed of primordial black holes. These black holes, if they exist, would have formed in the early universe, shortly after the Big Bang, from regions of space where density fluctuations caused parts of the universe to collapse into black holes. These primordial black holes could be much smaller than the black holes that form from collapsing stars, and if they exist in sufficient numbers, they could account for some or all of the dark matter in the universe. While this idea remains speculative, upcoming observations, including those from gravitational wave detectors, may help test the hypothesis. Dark matter plays a crucial role in shaping the universe's large-scale structure. It forms vast, invisible scaffolding upon which galaxies and galaxy clusters are built. Computer simulations of the universe's evolution, using models that include dark matter, show how galaxies form and evolve within giant cosmic filaments of dark matter. These simulations match the large-scale distribution of galaxies that we observe, further confirming the critical role dark matter plays in cosmic structure. If dark matter is the invisible framework holding the universe together, dark energy is the mysterious force that seems to be driving it apart. Discovered in the late 1990s, dark energy was invoked to explain the accelerating expansion of the universe. For much of the 20th century, astronomers believed that the expansion of the universe, first discovered by Edwin Hubble in the 1920s, should be slowing down due to the gravitational pull of all the matter in the universe. However, observations of distant supernovae in the late 1990s revealed a shocking discovery. Instead of slowing down, the expansion of the universe is speeding up. This acceleration suggests that some unknown force, dark energy, is driving the expansion. Dark energy is even more mysterious than dark matter. While dark matter at least interacts with gravity, dark energy appears to be an intrinsic property of space itself, acting like a kind of anti-gravity that repels matter and pushes space apart. It is often described as the energy of the vacuum. Empty space still has energy, and as the universe expands, more space is created, and therefore more dark energy is generated, accelerating the expansion further. One possible explanation for dark energy comes from Einstein's cosmological constant, a term he introduced into his equations of general relativity to explain a static universe. When it became clear that the universe was expanding, Einstein abandoned the cosmological constant, calling it his biggest blunder. However, with the discovery of dark energy, the cosmological constant has made a comeback, now reinterpreted as the energy density of space itself. While the cosmological constant is a simple explanation for dark energy, it raises deeper questions about why it has the specific value it does, and whether it is truly constant over time or varies in different regions of the universe. An alternative explanation for dark energy is the concept of quintessence, a dynamic, evolving form of energy that could change over time. Unlike the cosmological constant, quintessence would involve a new field that permeates space, similar to the Higgs field that gives particles mass. This field could evolve as the universe expands, causing the effects of dark energy to change over time. While this idea is appealing because it offers a more flexible explanation for dark energy, there is currently no direct evidence for quintessence, and it remains a speculative hypothesis. To better understand dark energy, astronomers are conducting large-scale surveys of the universe's expansion and the distribution of galaxies. Missions like the Dark Energy Survey (DES), the European Space Agency's Euclid satellite, and NASA's upcoming Nancy Grace Roman Space Telescope aim to map the distribution of galaxies and measure the expansion rate of the universe in unprecedented detail. By studying the cosmic web of galaxies and the growth of cosmic structures over time, these missions will test different models of dark energy and help determine whether it is truly constant or evolving. Understanding dark energy is critical not just for our knowledge of the universe's past, but also for predicting its future. If dark energy continues to drive the accelerated expansion of the universe, It could lead to a future where galaxies are so far apart that they become invisible to one another, effectively isolating galaxy clusters from each other in the so-called Big Freeze. In this scenario, the universe would continue expanding forever, becoming colder and darker as stars burn out and galaxies move beyond the reach of any observable influence. There are other more speculative scenarios for the universe's ultimate fate. If dark energy were to increase over time, it could lead to a big rip, in which the force of dark energy becomes so strong that it tears apart galaxies, stars, planets, and even atomic particles. Conversely, if dark energy were to weaken or reverse, the expansion could slow down or stop, potentially leading to a big crunch, in which the universe collapses back in on itself in a catastrophic reversal of the Big Bang. The study of dark matter and dark energy is pushing the boundaries of physics and cosmology, forcing us to confront questions about the very fabric of the universe. These mysterious components of the cosmos challenge our understanding of gravity, the nature of space and time, and the fundamental forces that govern the universe. As our observational tools become more sophisticated and our theoretical models more refined, we are slowly beginning to peel back the layers of these cosmic enigmas. Ultimately, solving the mysteries of dark matter and dark energy will require not only advances in technology and theory, but also new ways of thinking about the universe. It may be that our current understanding of physics is incomplete, and that discovering the true nature of dark matter and dark energy will require a radical shift in our perspective. Perhaps even a new understanding of space, time, and the fundamental structure of reality. As we continue to explore these profound questions, dark matter and dark energy remain at the frontier of human knowledge, inviting us to unlock the secrets of the universe and reshape our understanding of the cosmos. Each new discovery brings us closer to answering these fundamental mysteries and opens new doors to further exploration of the universe's most hidden realms. The quest to understand the dark side of the universe may ultimately lead to the most transformative scientific breakthroughs of the 21st century, with consequences for physics, cosmology, and our understanding of existence itself. As we continue our exploration of the universe's most profound mysteries, we are drawn to an even more speculative and visionary realm of science: the study of the multiverse. The concept of the multiverse, multiple universes existing alongside our own, is one of the most extraordinary and controversial ideas in modern physics and cosmology. It suggests that our universe, with its particular laws of physics, constants, and conditions, may be just one of an infinite number of universes, each with its own unique properties. While this idea might sound like science fiction, it has emerged as a serious hypothesis within theoretical physics, with implications that could revolutionize our understanding of reality. The notion of the multiverse arises from several areas of modern physics, including quantum mechanics, cosmology, and string theory. One of the earliest motivations for the multiverse comes from the concept of cosmic inflation, a theory that explains the rapid expansion of the universe in the moments immediately following the Big Bang. Inflation theory, proposed by physicist Alan Guth in the 1980s, describes a brief period of exponential growth that smoothed out the early universe, explaining why it appears so homogeneous and isotropic today. However, some versions of inflationary theory suggest that inflation didn't happen just once. Instead, inflation could be an ongoing process, creating new pocket universes with different physical conditions as it unfolds. This idea is known as eternal inflation, and it leads to the possibility that our universe is just one bubble in an endlessly expanding cosmic foam, with countless other universes forming in distant regions of space beyond our observable horizon. Each of these universes could have different physical constants, particle properties, and even different laws of physics altogether. One of the most famous proponents of this idea, cosmologist Andre Linde, developed the concept of chaotic inflation, which envisions a multiverse where new universes are constantly being born in different regions of space-time. According to Linde's theory, inflation never truly stops. It continues in some regions of space, while other regions slow down and form stable universes like ours. This process could produce a multiverse with an infinite variety of universes, each with its own distinct properties. The multiverse hypothesis also emerges from string theory, a theoretical framework that seeks to describe the fundamental nature of particles and forces. String theory suggests that the basic building blocks of reality are not point-like particles, but tiny, vibrating strings of energy. These strings can exist in multiple dimensions, up to 11 dimensions in some versions of the theory, far beyond the 3 spatial dimensions and 1 time dimension we experience. One of the most striking implications of string theory is that there may be a vast landscape of possible universes, each corresponding to a different configuration of the fundamental strings and extra dimensions. This string landscape could give rise to a multiverse where different regions of space contain different vacuum states, each with its own unique physical laws. Some of these universes might resemble our own, while others could be radically different, with entirely alien forms of matter, forces, and dimensions. The existence of such a landscape of universes is one of the reasons string theory is considered a candidate for explaining the multiverse, even though direct evidence of other universes remains elusive. Another area where the multiverse concept arises is in quantum mechanics, particularly through the many-worlds interpretation of quantum physics. Quantum mechanics, the branch of physics that deals with particles on the smallest scales, is famously weird. In the quantum realm, particles don't have definite states until they are observed. Instead, they exist in a superposition of states, meaning they can be in multiple places or states at once. When we measure a quantum particle, we observe one outcome, but what happens to the other possible outcomes? The many-worlds interpretation, proposed by physicist Hugh Everett in the 1950s, suggests that every time a quantum event occurs, the universe splits into multiple branches, with each possible outcome of the quantum event realized in a different universe. In this view, the entire universe is constantly branching into a vast tree of parallel realities, where every possible outcome of every event actually happens. In one branch of the multiverse, you might have turned left instead of right. In another, a different species may have evolved to dominate Earth. This interpretation of quantum mechanics is highly speculative and remains a topic of debate among physicists. However, it provides a striking vision of a multiverse that arises from the very nature of quantum reality. If the many-worlds interpretation is correct, then every choice, every chance event creates new universes with an infinite number of alternate realities existing side by side, each slightly different from the others. Despite the intriguing theoretical foundations for the multiverse, one of the biggest challenges facing multiverse theories is the lack of direct observational evidence. By definition, if other universes exist beyond our own, they would be separated from us by vast distances or even different dimensions, making them inaccessible to our current instruments and observations. Some physicists argue that the multiverse is, therefore, not a scientific hypothesis at all because it cannot be tested or falsified through experimentation, a key requirement for any scientific theory. However, there are some potential ways to test the multiverse hypothesis, at least indirectly. One possibility is that the bubble universes created by eternal inflation could occasionally collide with each other. If such a collision occurred between our universe and another, it might leave detectable imprints in the cosmic microwave background radiation, the faint afterglow of the Big Bang that permeates the universe. Researchers have already begun searching for such signatures, though none have been found so far. Another approach involves using the laws of physics themselves to make predictions about the multiverse. If the multiverse exists, it could help explain certain fine-tuning problems in physics. Questions about why the fundamental constants of nature, such as the strength of gravity or the cosmological constant, have the precise values they do. In our universe, these constants appear to be finely tuned for the existence of life, and if they were even slightly different, stars and galaxies might not form, and life as we know it would be impossible. The multiverse offers a possible solution to this puzzle. If there are an infinite number of universes, each with different physical constants, then it's not surprising that we find ourselves in a universe where the conditions are just right for life. After all, only in such a universe could intelligent observers exist to ask these questions. This idea, known as the anthropic principle, suggests that the apparent fine-tuning of the universe is not a mystery, but a natural consequence of the multiverse's diversity. Despite these theoretical motivations, the multiverse remains a deeply controversial topic. Some scientists argue that even if the multiverse exists, it lies beyond the reach of empirical science and may remain forever unobservable. Others suggest that future advances in physics, particularly in areas like quantum gravity and string theory, may eventually provide the tools we need to probe these hidden realms and test the multiverse hypothesis more rigorously. Even if we never find direct evidence for other universes, the study of the multiverse raises profound philosophical and existential questions. What does it mean to live in a universe that is just one of many? Are there other versions of ourselves living out different lives in parallel realities? And if the multiverse is infinite, does it mean that every possible event, no matter how improbable, happens somewhere? These questions challenge not only our understanding of science, but also our sense of identity and place in the cosmos. In recent years, the multiverse concept has also found its way into popular culture, inspiring works of fiction, films, and television that explore parallel realities and alternate timelines. While these portrayals are often fantastical, they reflect the growing fascination with the idea that reality itself might be far stranger and more complex than we ever imagined. The multiverse, with its infinite possibilities, taps into a deep human curiosity about what lies beyond the known and what might exist in realms beyond our perception. As physicists continue to explore the frontiers of the universe, the study of the multiverse remains one of the most speculative but exciting areas of research. It challenges our assumptions about the nature of reality and forces us to confront the possibility that our universe is just one small part of a much larger, more complex cosmic tapestry. Whether or not we ever find evidence of the multiverse, the very act of exploring these questions pushes the boundaries of human knowledge and imagination, expanding our understanding of the universe and our place within it. The pursuit of the multiverse is, in many ways, the ultimate expression of our desire to understand the cosmos. It represents the next great horizon in science, where the known laws of physics merge with the unknown possibilities of existence. As we venture deeper into this frontier, we may one day discover that the universe we inhabit is but a single chapter in an infinite story, a story that stretches across countless realms and realities, each more wondrous and mysterious than the last. As we venture even further into the conceptual and scientific boundaries of space and physics, we inevitably arrive at one of the most compelling yet complex questions of all: the search for intelligent life beyond Earth and the potential for communicating with extraterrestrial civilizations. This quest, which has captivated humanity for centuries, has evolved from myth and speculation into a serious scientific endeavor. It encompasses a broad range of fields, from astronomy and biology to physics and engineering, and stretches our imagination as we ponder not just whether we are alone in the universe, but what might happen if we encounter life that is both intelligent and technologically advanced. The search for extraterrestrial intelligence, SETI, has been a cornerstone of humanity's effort to answer one of its oldest questions. Are we the only intelligent beings in the universe? With the discovery of thousands of exoplanets over the past few decades, many of which are potentially habitable, this question has become more urgent and scientifically credible. Planets orbiting other stars, especially those in the so-called habitable zone, where conditions might support liquid water, are prime targets in the search for life. But finding microbial life is one challenge. Finding intelligent, technologically advanced civilizations capable of communication presents an entirely different set of challenges. One of the key strategies in the search for extraterrestrial intelligence is listening for signals, attempting to detect radio or laser transmissions from other civilizations. Since the mid-20th century, scientists have used radio telescopes to scan the skies for signals that might indicate the presence of intelligent life. The basic premise is that advanced civilizations, like ours, may use radio waves to communicate across interstellar distances, and if we are lucky, we might intercept one of their transmissions. The SETI Institute, one of the leading organizations in this field, has been using radio telescopes to search for such signals for decades, with large-scale projects like the Allen Telescope Array scanning thousands of stars for potential signs of extraterrestrial technology. The rationale behind using radio waves for SETI is simple. Radio waves travel at the speed of light and can pass through interstellar gas and dust with minimal interference, making them an ideal medium for long-distance communication. However, despite over half a century of listening, no definitive extraterrestrial signal has been detected. This lack of success has led to a deeper understanding of the complexities and challenges involved in detecting signals from alien civilizations. One of the key challenges is the vastness of space. The Milky Way galaxy alone contains an estimated 100 billion stars, and beyond our galaxy lie trillions more galaxies. Even if intelligent civilizations are relatively common, the odds of detecting a signal from one of them are low, simply because of the immense distances and the fact that we have only just begun to scratch the surface of what could be a cosmic sea of potential signals. Additionally, intelligent civilizations might not use radio waves for communication at all. They could use more advanced technologies or methods that we have yet to discover. In recent years, some researchers have proposed alternative methods for searching for extraterrestrial intelligence. One promising idea is the use of optical SETI, which involves looking for powerful laser pulses rather than radio waves. A sufficiently advanced civilization might use laser technology for communication or other purposes, and such lasers could be detectable by Earth-based telescopes. Optical SETI focuses on finding brief, intense bursts of light that could indicate an artificial source. This method has the advantage of being able to detect very narrow, focused beams of light, which could carry more information than radio waves and be easier to detect across vast distances. Another emerging field is the search for technosignatures, indirect evidence of advanced technology on distant worlds. While traditional SETI searches for direct signals like radio waves or laser pulses, technosignature searches look for signs of large-scale technological activities that might be observable from Earth. For example, a highly advanced civilization might build megastructures like Dyson spheres, hypothetical constructs that surround a star and capture its energy output. Such structures would affect the star's light in observable ways, creating a signature that astronomers could detect. Similarly, technosignatures might include pollution in a planet's atmosphere, artificial illumination, or other forms of large-scale engineering. The search for technosignatures is still in its early stages, but it represents a promising avenue for SETI, especially as our ability to detect and analyze distant planets improves. NASA's upcoming missions, such as the James Webb Space Telescope and the proposed LUVOIR, Large Ultraviolet Optical Infrared Surveyor, telescope, could provide unprecedented data on the atmospheres and surface conditions of exoplanets, allowing us to look for signs of technology, such as unusual chemical compositions or infrared emissions that don't fit natural explanations. Despite the lack of success in finding extraterrestrial signals so far, there are many reasons to believe that intelligent life could exist elsewhere in the universe. One of the most compelling arguments comes from the sheer scale of the cosmos. The famous Drake equation, proposed by astronomer Frank Drake in 1961, attempts to estimate the number of detectable civilizations in our galaxy based on factors such as the rate of star formation, the number of stars with planets, and the likelihood that intelligent life will arise and develop technology. While the exact values of many of these factors are still unknown, the discovery of thousands of exoplanets has dramatically increased the likelihood that planets capable of supporting life are common. The Drake equation is often used to frame discussions about the Fermi paradox, the apparent contradiction between the high probability of extraterrestrial civilizations and the lack of evidence for their existence. If intelligent life is common, the logic goes, we should have detected some sign of it by now. So why haven't we? This paradox has inspired a wide range of possible explanations, some hopeful and others unsettling. One potential explanation is that intelligent civilizations are extremely rare, perhaps because the conditions for life to develop into complex, technological societies are much more difficult than we realize. This idea, known as the Great Filter hypothesis, suggests that somewhere in the development of life, either at the beginning with the formation of simple life forms or much later with the evolution of intelligence, there is a critical barrier that is rarely crossed. If the Great Filter is in our past, then we may be one of the few intelligent civilizations to have emerged. However, if the great filter lies in our future, perhaps in the form of catastrophic challenges like environmental collapse, nuclear war, or other existential risks, then our own survival might be at stake. Another possibility is that intelligent civilizations are out there, but choose not to communicate or make themselves known. This could be because they are following a policy of non-interference, similar to the Prime Directive in science fiction, or because they believe that revealing their presence could be dangerous. Some scientists have speculated that civilizations might become reclusive after reaching a certain level of technological advancement, preferring to focus inward rather than expand across the stars. This idea is often referred to as the zoo hypothesis, which suggests that advanced civilizations are observing us from a distance but deliberately avoiding contact. Alternatively, intelligent civilizations might be communicating in ways that we are currently incapable of detecting. They might use technologies or communication methods that are so far beyond our own that we wouldn't recognize them even if they were right in front of us. Just as ancient humans would have had no way of understanding radio waves, we might be similarly blind to advanced forms of communication or information transmission used by extraterrestrial civilizations. As the search for extraterrestrial intelligence continues, it is also important to consider what might happen if we do detect a signal from an intelligent civilization. How would humanity react to the knowledge that we are not alone in the universe? What protocols should we follow in responding to such a signal? And what ethical considerations should guide our interactions with extraterrestrial life, particularly if the civilization is more or less advanced than our own? The discovery of intelligent life beyond Earth would be one of the most significant events in human history, reshaping our understanding of the universe, our place in it, and the nature of life itself. It could bring both incredible opportunities and profound challenges. On the one hand, contact with an advanced civilization could lead to a transformative exchange of knowledge, technology, and culture. On the other hand, there are risks associated with such contact, particularly if the intentions or nature of the extraterrestrial civilization are unknown. To prepare for this possibility, organizations like the SETI Institute, the United Nations, and various space agencies have developed protocols for how to handle the discovery of extraterrestrial intelligence. These protocols include guidelines for verifying the authenticity of a signal, alerting the international community, and determining whether and how to respond. However, the specifics of how humanity would react to such a discovery remain largely speculative. For now, the search for extraterrestrial intelligence continues, driven by the tantalizing possibility that we might one day make contact with another civilization. Whether through traditional radio signals, advanced techno-signatures, or even entirely new forms of communication, the quest to find intelligent life beyond Earth remains one of the most profound and exciting challenges in modern science. As we look to the stars, we are reminded of the vastness of the universe and the potential for discoveries that could change the course of human history. The search for other minds in the cosmos is not just a scientific endeavor. It is a search for connection, for understanding, and for a deeper sense of our place in the great cosmic expanse. As we continue to ponder the possibility of intelligent life beyond Earth, we enter yet another deeply fascinating chapter of space exploration and science, the future of human space colonization. The idea of humanity expanding beyond Earth to establish permanent settlements on other planets and moons is not just a vision from science fiction. It is increasingly becoming a serious goal for space agencies, private companies, and forward-thinking visionaries. With the Moon, Mars, and even more distant celestial bodies in our sights, the next century could witness humanity's first steps toward becoming a multiplanetary species. This goal raises profound questions about the technical challenges of space colonization, the ethical and political implications, and what it means for the future of humanity. The colonization of space is often framed as a solution to some of Earth's most pressing issues: overpopulation, resource depletion, and the existential risk of global catastrophes like nuclear war, climate change, or asteroid impacts. By establishing self-sustaining colonies on other planets, humanity could ensure its survival in the event of a planetary disaster. Moreover, space colonization could open up new opportunities for scientific research, technological innovation, and economic growth, particularly through the exploitation of space resources. The most immediate and realistic target for human colonization is the Moon. Since the Apollo missions of the 1960s and 1970s, the Moon has remained a focal point for space exploration, and interest in returning to the lunar surface has surged in recent years. NASA's Artemis program aims to return humans to the Moon by 2024, with the long-term goal of establishing a sustainable human presence on the lunar surface. Artemis is seen as a stepping stone for future Mars missions, allowing scientists and engineers to test technologies and systems in a more accessible environment before tackling the greater challenges of Mars. The Moon offers several advantages as a starting point for human space colonization. It is relatively close to Earth, making it easier to transport supplies and personnel. The Moon's lower gravity, about 1/6 of Earth's, reduces the energy required for launching spacecraft and constructing infrastructure. Additionally, the Moon is rich in resources, such as water ice at its poles, which could be used for life support, fuel production, and building materials. In situ resource utilization, ISRU technologies will play a critical role in making lunar colonization feasible by allowing colonists to use local materials to produce oxygen, water, and even metals for construction. NASA, along with other space agencies and private companies like SpaceX, is working on developing the technology necessary for long-term lunar habitation. This includes building habitats that can protect astronauts from the harsh conditions on the Moon's surface, such as extreme temperature fluctuations, radiation, and micrometeorite impacts. Concepts like underground habitats, inflatable habitats, or structures built using 3D printing with lunar regolith, moon soil, are being explored. Additionally, the development of new propulsion technologies, including reusable rockets, is making space travel more cost-effective and sustainable. Beyond the Moon, Mars represents the next great frontier for human colonization. Mars has long been the focus of scientific and popular imagination, and it is widely considered the most viable location for a self-sustaining human colony in the solar system. With its day length similar to Earth's and evidence of liquid water in its distant past, Mars offers a tantalizing possibility for human habitation. However, the challenges of colonizing Mars are far greater than those of the Moon. The journey to Mars takes about 6 to 9 months, depending on the alignment of the planets, and communication delays can range from 4 to 24 minutes due to the distance between Earth and Mars. One of the biggest challenges on Mars is its thin atmosphere, which is composed mostly of carbon dioxide. While the presence of CO2 could be useful for producing oxygen through processes like electrolysis, the atmosphere provides little protection from solar and cosmic radiation. Any human settlement on Mars would need to be shielded from this radiation, likely through underground habitats or the use of regolith for radiation protection. Mars' surface temperature is also extremely cold, averaging about -80 degrees Fahrenheit, -60 degrees Celsius, and dust storms can cover the planet for weeks at a time, further complicating efforts to establish a stable environment for human life. Despite these challenges, plans for Mars colonization are moving forward. SpaceX, led by Elon Musk, is perhaps the most high-profile organization working toward this goal. Musk has outlined an ambitious vision for creating a self-sustaining city on Mars within the next few decades. His company is developing the Starship spacecraft, a fully reusable rocket designed to carry large crews and cargo to Mars and other destinations in the solar system. SpaceX's long-term goal is to make life multiplanetary by establishing a colony on Mars that can grow and thrive independently of Earth. NASA is also working on Mars exploration, with plans to send astronauts to the Red Planet in the 2030s. The success of these missions will depend on the development of new technologies, such as advanced life support systems, habitats that can withstand the Martian environment, and propulsion systems capable of reducing travel time between Earth and Mars. Robotic missions like the Perseverance rover, which is currently exploring Mars and preparing for a sample return mission, are providing crucial data that will inform future human exploration efforts. In addition to the technological challenges, there are significant ethical and political questions surrounding space colonization. One of the primary concerns is the environmental impact of human activities on other planets. Just as we are grappling with the consequences of environmental degradation on Earth, we must consider how human colonization could affect the ecosystems of other planets. While Mars and the Moon are not known to host life, future missions could explore worlds that do, such as Europa or Enceladus, moons of Jupiter and Saturn that are thought to harbor subsurface oceans and potentially even microbial life. Protecting these environments from contamination by Earth-based organisms is a key consideration for planetary protection efforts. There are also questions about governance and ownership in space. The Outer Space Treaty of 1967, signed by over 100 countries, establishes that space is the province of all mankind and that no country can claim sovereignty over the Moon or any other celestial body. However, as private companies and nations increasingly focus on resource extraction and settlement in space, new legal frameworks will be needed to address issues of property rights, resource use, and the responsibilities of spacefaring entities. International cooperation and regulation will be crucial to ensuring that space exploration is conducted in a way that benefits all of humanity and avoids conflicts over resources. Another important consideration is the social and psychological challenges of space colonization. Living on another planet, far from Earth, will place immense strain on the mental health and well-being of colonists. Isolation, confinement, and the dangers of space travel will create unique psychological challenges that must be addressed through careful mission planning and support systems. Astronauts on the International Space Station, ISS, already deal with many of these issues, but the duration and distance of a Mars mission or permanent lunar settlement would amplify these challenges. One of the most profound implications of space colonization is the potential for human societies to evolve in radically different ways on other planets. If human colonies become self-sustaining and eventually independent from Earth, they could develop new cultures, economies, and political systems. Mars, with its lower gravity and harsh environment, could give rise to a distinct Martian identity, with values and priorities shaped by the unique challenges of life on the Red Planet. The socio-political dynamics of these new societies could diverge significantly from those on Earth, raising questions about how these colonies would relate to Earth and whether they would seek autonomy or even independence. In the more distant future, human colonization could extend beyond Mars to the moons of the outer planets, asteroids, and even habitats in deep space. Technologies like space habitats, artificial structures that simulate Earth-like conditions, could allow humans to live in space indefinitely, even in regions far from any planet. These habitats could be built in orbit around the Earth, Moon, Mars, or even in the asteroid belt, providing a platform for research, industry, and human settlement. Asteroids, in particular, offer a wealth of resources that could fuel human expansion into the solar system. Many asteroids contain valuable metals like iron, nickel, and platinum, as well as water and other essential materials. Mining asteroids could provide the raw materials needed to build space habitats, spacecraft, and infrastructure, reducing the need to transport these resources from Earth. Companies like Planetary Resources and Deep Space Industries have already begun exploring the feasibility of asteroid mining, and future missions could establish the foundations for a new space-based economy. Looking even further ahead, the development of advanced propulsion technologies could one day allow humans to venture beyond the solar system and explore other star systems. While this remains speculative for now, the discovery of potentially habitable exoplanets around stars like Proxima Centauri and the development of interstellar propulsion concepts, such as Breakthrough Starshot, offer tantalizing glimpses of what the future might hold. If humans can survive and thrive on Mars and other planets, interstellar colonization could be the next step in our evolution as a spacefaring species. The future of space colonization is both exciting and daunting, filled with challenges and opportunities. It is a journey that will require the collaboration of scientists, engineers, policymakers, and the global community. As we prepare to take our first steps beyond Earth, we are not just expanding the frontiers of exploration. We are laying the foundation for a future where humanity is no longer confined to a single planet. The challenges are immense, but the rewards, both for survival and for the advancement of knowledge and civilization are potentially infinite. In the coming decades, as humans establish a permanent presence on the moon, set foot on Mars, and possibly explore even more distant worlds, we will begin to redefine what it means to be human. Space colonization is not just about surviving on other planets. It is about expanding our horizons, pushing the boundaries of our understanding, and embracing the vast potential of the cosmos. The future of humanity may lie among the stars, and our journey there is only just beginning. If you like the video, then consider clicking on the recommendation and watch our other videos. Be sure to subscribe and see you on our next interstellar trip.